Let's take advantage of this journey through the stars to observe some beautiful objects in the universe relatively close to us. The closest star system to ours has been named by astronomers Alpha Centauri. We are only 4.3 light-years away from Earth. Originally, Alpha Centauri was organized around a double star, the stellar couple Alpha Centauri AB. These two stars were named by astronomers Alpha Centauri A, or Rigil Kentaurus, and Alpha Centauri B, Ptolemaeon. Today, what you have in front of you is a triple system, because the stellar pair captured the star Proxima Centauri, or Proxima of the Centaur, as it passed by. Alpha Centauri A is a yellow dwarf star like our Sun, but it is even bigger than the Sun. 10% more massive, it has a radius 23% larger than our star. It is, as you can see, the brightest star in the triple system. As for Alpha Centauri B, it is an orange dwarf, so it has a smaller size and mass than its companion star, so it is logically less luminous. Alpha Centauri A and B orbit together for 80 years. They are gravitationally bound. The last star of this triple system, Proxima Centauri, has been the closest star to the Sun for 32,000 years. It will remain so for at least that long. But remember that the universe is constantly in motion. Before it, another star was closer to our Sun, and after it, it will be another one. Proxima Centauri is a fascinating star. It is a red dwarf star, not very massive and not very bright. It has a mass 8 times smaller and a radius 6 times smaller than the Sun. Now that it is part of the Alpha Centauri triple system, it has been named Alpha Centauri C by astronomers. Although Proxima Centauri is gravitationally bound to the stellar pair Alpha Centauri AB, you will not see it from Earth, whereas you can distinguish the pair Alpha Centauri AB very well with the naked eye in the southern sky. This seems logical when you know that this star, discovered only in 1915, has a luminosity of only 0.006% of that of the Sun. Proxima Centauri is surrounded by planets, just as our Sun is surrounded by the planets of our solar system. The exoplanet Proxima Centauri B, which orbits Proxima Centauri, is of particular interest to scientists, who call it an exotherm. It is the closest exoplanet to us. Moreover, because it is located in the temperate zone of its star, is rocky, like the Earth, and of a size comparable to our planet, nothing prevents it from being habitable. Furthermore, observations have shown the presence of dust belts containing rock and ice fragments around Proxima Centauri, similar to the asteroid belt and the Kuiper belt in our solar system. This could mean that Proxima Centauri is probably home to more than one planet. While the imaginations of scientists and writers have been fired up about the Alpha Centauri star system, we have not yet been there. Even though Proxima Centauri is the closest star to the Sun, it is still more than 40,000 billion kilometers, or 25,000 billion miles away. The James Webb Telescope itself will not be able to produce images of the surface of stars located so far away, while Proxima Centauri is the closest to us after the Sun. You will tell me that we can send a probe there? Yes, but with current technology, even a probe like Voyager 1 would take more than 70,000 years to reach Alpha Centauri. We will therefore have to wait for the launch of the Future Giant Telescope, ELT of ESO in Chile around 2027 to know more about this star system. Unless a project announced in 2016, the Breakthrough Starshot will see the light of day. This project aims to find a way to launch tiny probes weighing only 1 gram into space, propelling them with laser beams to give them more speed. This technique could allow them to reach 20% of the speed of light, or 60,000 kilometers per second, or 37,000 miles per second. These small probes could thus reach the Moon in 7 seconds, and the Alpha Centauri star system in only 20 years. But even if these probes could travel to Alpha Centauri, would their very small size allow them to send back relevant information to Earth? It is true that the question of the return of the information collected by the probes is rather thorny. Even if they were to travel at the speed of light, the information would take 4 years to reach us from Alpha Centauri. Let's continue our journey through space to reach the star Sirius, located 8.6 light-years from Earth in the constellation of the Great Dog. Sirius A, with its scientific name Alpha Canis Majoris, is the brightest star in our night sky and the 5th closest star to the solar system. You're probably wondering how you can see Sirius so well from Earth without even needing a telescope, while Proxima Centauri, the closest to us after the Sun, is not visible. This is simply because Sirius is a very massive star. It is 1.8 times larger than the Sun, and 2.3 times more massive. Its surface temperature is estimated at more than 9,600 degrees Celsius, or 17,300 degrees Fahrenheit. The star Sirius A has a much smaller companion star, Sirius B. This white dwarf star, which is about the size of the Earth, has a mass equivalent to the Sun. Sirius B was discovered in 1862, a discovery that marks the first in the history of astronomy. It is separated from Sirius A by a distance of about 20 astronomical units, or 20 times the distance between the Earth and the Sun, which is equivalent to the distance between the Sun and Uranus, for example. Its orbit is elliptical and lasts 50 years. The 2 Sirius stars are therefore more or less distant, depending on the year. In 2025, it will be the largest possible separation between the 2 stars. Moreover, Sirius A is moving away from us, albeit very slowly. In the 17th century, the astronomer Edmund Halley compared the position of Sirius in the night sky to the position recorded by the astronomer Hipparchus in the 2nd century BC. In 18 centuries, the star has moved about 30 arc minutes, the size of the full moon. It may surprise you that the existence of Sirius was already known in the Hellenistic era. It is even the Greeks who gave it its name. Sirius comes from the Greek Syros, the fiery or burning one. If we look at the history of astronomy, it is not so surprising, because already the Babylonians observed the sky 3,000 years before our era. And Sirius A is so bright that you can't miss it. This star has fascinated people over the centuries. In ancient Egypt, it was associated with the goddess Isis, the wife of Osiris, and one of the 5 children of Nut in the sky, and Geb was the god of the earth. Moreover, the heliacal rising of Sirius, that is to say, the movement when it was the last star to shine before the sunrise, coincided with the summer solstice and the fertile floods of the Nile. It may also be interesting to know that the heliacal rise of Sirius has shifted in time. Indeed, the axis of rotation of the Earth describes a cone in space in 25,800 years. At this moment, the axis of rotation points to the North Star, which is used to indicate the North Pole. But it has not always been so. Over the centuries, this role has been assumed in turn by the star Kochab of the Little Dipper at the time of Homer, and by Thuban, or Alpha of the Dragon, at the time of the construction of the pyramids. In 10,000 years, it will be the star Vega in the constellation of Lyra that will show us north. Before we continue our journey, here are some tips for seeing the star Sirius the next time you look at the stars from Earth. The star Sirius is visible throughout the winter in the constellation of the Great Dog. It can be seen from anywhere on Earth. If you are in the northern hemisphere, the star is part of the winter hexagon. To help you find the brightest star, you can use the 3 stars in Orion's belt, also called the 3 Magi. They point in the direction of Sirius. Just draw a line from these 3 stars. Sirius should not be difficult to spot, since it is much brighter than the others. With a 400mm telescope at least, you can also see the white dwarf Sirius B. One last tip. Sirius is rather low in the sky. The light emitted by the star must therefore cross a great distance of atmosphere to reach us. The turbulence in the atmosphere can produce a flickering effect. That's why sometimes you can get the impression that Sirius is flickering a bit, like an airplane crossing the sky. We are now 35 light-years away from our solar system. The exoplanet in front of you must look familiar. That's normal. It's the closest exoplanet ever photographed in direct view. It is also one of the few exoplanets ever photographed. The picture you have probably already seen was published by a team of researchers from the University of Hawaii on July 6, 2021, in the journal, the Astrophysical Journal Letter. Coconuts 2b is a gas giant like Jupiter. It orbits a star named Coconuts 2a, or L3426. Coconuts 2a is a red dwarf with a mass equivalent to 1/3 of that of the Sun, with a fast rotation period of 2.83 days. The Coconuts 2a star system is quite young and is estimated to be between 150 and 800 million years old, as is the exoplanet Coconuts 2b. For comparison, our Sun is 4.6 billion. It was detected in 2011 by the WISE satellite and then studied through the Coconuts program, which analyzes the characteristics of celestial objects and distant star systems. In 2011, the data received by the WISE satellite suggested that Coconuts 2b was a celestial object drifting in space with no particular orbit. 10 years later, it was concluded that the exoplanet does orbit a star, with an orbital period of more than 1 million years, which is huge. This can be explained by the great distance between this planet and its star, 6,471 astronomical units, which is more than 6,000 times the distance between the Earth and the Sun. Moreover, Coconuts 2b being very far from its star, it is a gaseous planet with an average temperature of 161 degrees Celsius or 320 degrees Fahrenheit. It makes one revolution around its star, in addition to the one around the Sun. Fortunately for us, this distance allowed us to obtain a direct image of it without the planet being drowned by the light of its star. Another impressive fact: Coconuts 2b has a mass 6 times greater than that of Jupiter. To give you an idea, Jupiter is already 317 times the mass of the Earth. Coconuts 2b is qualified as an extreme star because of its colossal mass. The extreme stars are all the stars whose characteristics are so singular that they seem inconceivable. Coconuts 2b is thus the second largest exoplanet discovered to date. Let's continue our journey to K2-18, the star system that could host another Earth. We are now 63 light-years from Earth, in the constellation of Pisces. This is where we find the coldest star in the universe, WD 0806 661b. Stars are, by definition, hot bodies. They are made of hot gas, and like a constantly burning engine, they constantly consume energy by emitting heat. The star in front of you holds the record as the coldest star in the universe. It is a brown dwarf star with a surface temperature between 27 and 80 degrees Celsius, or between 80 degrees Fahrenheit and 180 degrees Fahrenheit, temperatures close to those of the Earth. As you can imagine, cold stars are not that common in the universe. The Sun is not the hottest star, and yet its temperature is 6,000 degrees Celsius, or 10,800 degrees Fahrenheit, at its surface, and 15 million degrees Celsius, or 27 million degrees Fahrenheit, at its core. It must be said that brown dwarfs are hardly considered as stars. Their formation is similar to that of a star. That is why they are considered as stars. But they are at the limit between a small cold star and a large hot planet. WD 0806 661b is 6 to 9 times more massive than Jupiter. Categorized as an ultra-cold dwarf because its temperature is below 2,400 degrees Celsius, or 4,350 degrees Fahrenheit, WD 0806 661b, by its mass, is at the limit with the supergiant planets. By definition, a star must have a sufficient mass to trigger the nuclear fusion of hydrogen in its core. The fusion of hydrogen atoms in the core of a star releases a large amount of heat and light, powering the star like a huge engine throughout its life. The minimum mass for this process to occur is about 80 times the mass of Jupiter, or 10% of that of the Sun. Planets do not have a mass large enough to trigger this kind of reaction. But brown dwarfs are very large planets, between 10 and 80 times more massive than Jupiter. They are thus massive enough to allow the fusion of deuterium, also called heavy hydrogen, but not hydrogen. The structure of deuterium facilitates its fusion, despite the relatively low mass of brown dwarfs. Too big to be part of the category of planets, and too small to fit in that of stars, brown dwarfs form a separate category, hence the nickname of failed star. But if brown dwarfs are given a sad nickname, it should not be deduced that their knowledge is of no interest. NASA explains that brown dwarfs could occupy an important part of the mass in the universe. Given that they are not very luminous, it is perhaps towards them that we should turn to finally solve the thorny problem of the missing mass. A mass whose influence is suspected, but that we have not yet managed to detect. Let's continue our journey towards K2-18b. We are now 84 light-years away from Earth. Have you noticed this strange starless planet, which seems to float alone in the universe? It is the exoplanet PSO J318.522. In 2013, an international team of astronomers announced in the journal Astrophysical Journal Letters that they had discovered a lonely world through the Pan Stars 1 telescope installed near Haleakala in Hawaii, a gaseous exoplanet that orbits no star. Is this even possible? This announcement has shaken the scientific community because never before has an object floating freely in space been discovered. The mystery is even thicker as PSO J318.522 has all the characteristics of young planets orbiting other stars: mass, color, and energy. Astronomers have estimated that this strange planet belongs to a collection of stars, the Beta Pictoris moving group, which formed about 12 million years ago. It is therefore very young on the scale of the universe. It is massive, since it is 6 times the mass of Jupiter. It is, however, the lowest mass ever observed for a free-floating body. PSO J318.522 was discovered in 2010, and it is in 2013 that its discovery was confirmed. Astronomers were then studying brown dwarfs, the objects of which we observed a specimen just before. The telescope had been set to detect the faint red glow of brown dwarfs, and it was an exoplanet with a very red spectrum that was discovered. By the way, the spectra of brown dwarfs and gas giants are similar, and the confusion is often made between these two celestial objects. The young planet, PSO J318.522, was observed by a direct observation method. Generally, planets found by direct detection are difficult to study because they are located next to much brighter stars. But since PSO J318.522 is not located near a star, its observation will be facilitated, which can give scientists a lot of information about the internal mechanisms of giant gas planets. Since that discovery, other solitary exoplanets have been found, including CFB-DSIR 2149-0403, which was discovered in 2012 by a team of researchers at the University of Montreal and described as a planetary mass-free object, or brown subdwarf. So how have astronomers explained these wandering planets since these discoveries in the early 2010s? One theory states that these planets would have been ejected from their home systems. There could be smaller planets nearby, such as Earth, that current technologies do not allow us to detect. Let's continue our journey in the universe with another strange exoplanet, TOI 1452b, a super-Earth-like exoplanet that is suspected to be an ocean planet. First of all, it is necessary to understand the term of super-Earth. It designates an exoplanet which has a mass between that of the Earth and that of a giant planet. The mass of a super-Earth is thus between 1 and 5 times the mass of the Earth and 10 times the mass of the Earth. Be careful, a super-Earth is not necessarily a planet that could harbor life. Only the mass is taken into account to qualify an exoplanet as a super-Earth, without taking into account the other conditions necessary to harbor life, such as the presence of water and the composition of the atmosphere, for example. TOI 1452b is a super-Earth located at 100 light-years from Earth in the Dragon constellation. It orbits in the habitable zone of a red dwarf, located in a binary system. Its star is therefore smaller than the Sun, which is a yellow dwarf. Spotted by the NASA TESS telescope, TOI 1452b was then observed with powerful instruments. These observations showed that it could be an ocean planet, i.e. a planet covered with a vast and deep layer of water. TOI 1452b has been detected thanks to the transits method, which consists in measuring the light of a star in search of possible decreases of luminosity. A small decrease in brightness at regular intervals is a reliable indication of the presence of an exoplanet orbiting the star, because when the planet passes in front of its star, it occults the star, which causes this decrease in brightness. TOI 1452b passes in front of its star every 11 days. The data collected and analyzed showed that this planet is about 70% larger than the Earth, with a mass of 5 times that of our planet. The solar system of TOI 1452b is said to be binary because it has 2 stars separated by 97 astronomical units, or 2.5 times the distance between the Sun and Pluto. It is around the larger of the 2 stars of this binary system that the ocean planet orbits. An article published in the Astronomical Journal indicates that TOI 1452b is a rocky planet, but with a density less than that of the Earth. The Earth has very little water compared to its mass. Indeed, water represents less than 1% of its mass. Unlike other stars, such as the satellites of Jupiter, Ganymede, and Saturn, Titan and Enceladus, the liquid water on these moons represents from 16 to 46% of the total volume. There is more liquid water inside Europa, Ganymede, and Titan than on Earth. Astronomers are leaning towards the hypothesis that the relatively low density of TOI 1452b is linked to the presence of a lot of water, especially since this planet is neither too close nor too far from its star, which would allow the appearance of water in liquid form. According to estimates, water could constitute 30% of the mass of TOI 1452b, as on the moons Ganymede and Enceladus. There are other exoplanets that are called ocean worlds because of their density, but TOI 1452b is definitely the most interesting because it is relatively close to us. The James Webb Telescope, put into orbit in December 2021, should give even more information on this ocean planet, which is only 100 light-years away from Earth. We will then be able to confirm whether or not TOI 1452b is an ocean planet. It is time for us to leave behind this mysterious planet. We finally arrived in the star system K2-18. It's been a long journey, but you won't regret embarking on this journey in search of the most promising planet for an alien life form. We are 124 light-years from Earth in the constellation Leo. The K2-18 star system you are looking at is also known as EPIC 201912552. This planetary system is organized around a red dwarf, and it has at least 2 planets, a hot super-Earth called K2-18c, and a smaller, Neptune-like planet called K2-18b. The central star of the K2-18 star system is a red dwarf. Smaller than the Sun, it is about 1/3 of its mass. its luminosity is only 3% that of the Sun. The surface temperature of this red dwarf is 3,220 degrees Celsius, or 5,800 degrees Fahrenheit, half that of our Sun. It takes about 39 days to make a complete turn on itself, against 25 days for the Sun at the equator, and 36 days at the poles. The star K2-18 is located 124 light-years from Earth, which makes K2-18 a relatively close star system. You surely realized this when you came here. Between the Sun and the red dwarf K2-18, there are only about 15,000 stars. The star K2-18 is very different from the Sun, and not only for reasons of mass, temperature, or rotation on itself. It is a red dwarf, a completely different class of star than the Sun, which is a yellow dwarf. Before continuing to explore the K2-18 star system, let's start by examining this red dwarf. The first red dwarfs were discovered in the 20th century. Proxima Centauri, which we observed earlier, was discovered in 1915, followed by Barnard's star, almost 6 light-years away from our Sun. Red dwarfs are the smallest stars. Their mass is between 8 and 40% of that of the Sun. They are also the most frequent stars. More than 75% of the stars in the Milky Way are red dwarfs, 160 billion out of 300 billion. Moreover, among the 30 nearest stars, 20 are red dwarfs. It is believed that there are billions of super-terrestrial stars orbiting red dwarfs in the Milky Way alone. No red dwarf is visible to the naked eye from Earth, for the simple reason that they are not bright enough. Red dwarfs have, on average, a luminosity equivalent to 1% of that of the Sun. The largest of them can reach 3 to 4% of the Sun's luminosity, not more. Not very massive, red dwarfs are not very hot, and their temperature is always lower than 3,730 degrees Celsius, or 6,700 degrees Fahrenheit. According to astrophysicist models, and given their physical properties, red dwarfs would be likely to shine relatively constantly for hundreds of billions of years, several tens of times the age of the universe. All the red dwarfs that we observe today are only at the beginning of their existence. While some of them, like the red dwarf Proxima of the Centaurus, will shine for more than 1,000 billion years, our Sun will slowly die out in 8 billion years by transforming into a white dwarf. This is enough to make you dizzy. We must not confuse red dwarfs and white dwarfs, which are the corpses of small stars, whose light is extinguished after several billion years. To make it clearer, I will tell you about the Hertzsprung-Russell diagram, which was developed in the early 20th century. The Hertzsprung-Russell diagram classifies stars according to their absolute brightness. This luminosity depends on several factors: the mass of the star and the temperature at the surface. The more massive a star is, the stronger its brightness. Each star does not have a fixed place on this diagram. Remember that the universe and its objects are constantly evolving. The initial mass of the star determines its placement on the diagram, but also its evolution. There are several groups of stars: main sequence stars, white dwarfs, blue giants, red giants, and supergiants. Stars will move from one group to another during their evolution. Let's take the example of the Sun. The Sun is a yellow dwarf. It is currently located in what is called the main sequence of the diagram. The stars of the main sequence are those inside which hydrogen alone is consumed by nuclear reactions. The consumption of hydrogen produces helium, which in large quantities will hinder the nuclear reactions in the heart of the star. When the star has consumed 10 to 20% of its total hydrogen, it will begin to collapse. A nuclear fusion reaction occurs, and the star will swell while cooling. It is at this point, when the drop in temperature results in a red shift, that the Sun will become a red giant. Over billions of years, the star will gradually die out. When the Sun has reached a very low temperature and can only radiate the remaining heat, it will become a white dwarf, the ultimate stage of stellar evolution, before cooling completely, billions of years later, to become a black dwarf. As for red dwarfs, they have a longer lifespan than the Sun. They can consume a larger proportion of hydrogen because the conversion of hydrogen into helium is very slow. In addition, helium does not accumulate in the center of the star, but circulates inside. Red dwarfs will never become red giants because they heat up slowly until all the hydrogen is consumed. Since the Big Bang, there has not been enough time to observe the terminal sequence of a red dwarf, and yet about 13.8 billion years have passed. The K2-18 star system is home to at least 2 exoplanets, K2-18b and K2-18c, which orbit the star K2-18. Both are more massive than the Earth. They are rocky superterrestrials, with a mass of 7 and 8.6 times that of the Earth. The closest planet to the star K2-18 is K2-18c. This hot super-Earth was discovered in 2017 and confirmed in 2018. It was in fact by studying K2-18b, which had been discovered earlier in 2015, thanks to the American satellite Kepler, that the researchers spotted the signal of K2-18c and were able to discover this exoplanet. K2-18b is indeed the one that interests astronomers the most. It is the most distant from the star K2-18. It is between 6 and 10 masses of the Earth, and its radius is 2.3 times larger than that of our planet. It has an orbital period of 33 days and an equilibrium temperature of about minus 23 degrees Celsius, or minus 9.4 degrees Fahrenheit, which is very close to the Earth's equilibrium temperatures of minus 18 degrees Celsius, or minus 0.4 degrees Fahrenheit. As a reminder, the equilibrium temperature of a planet is the theoretical temperature of its surface in the absence of an atmosphere. Astronomers believe that K2-18b has all the characteristics to possess liquid water on its surface, which would make it habitable. Its density, however, seems far too low for it to be a rocky planet. Either K2-18b is a rocky planet with liquid water on its surface, or it is a planet covered by a thick layer of ice. In other words, it is a rocky super-Earth, surrounded by a small gaseous envelope, or a gaseous mini-Neptune, essentially composed of water and covered with ice. In any case, K2-18b is made up largely of so-called volatile constituents, which form a fluid envelope with elements like molecular hydrogen, helium, or water. As often in the observation of the universe, nothing is certain yet. These two hypotheses hold true, and only the observations of the James Webb Telescope can tell us more. Indeed, the telescope is capable of analyzing the atmosphere of exoplanets, as it proved with the exoplanet WASP-39b, I remind you that James Webb has demonstrated the presence of CO2 in the atmosphere of WASP 39b, a hot gaseous planet located 700 light-years away in the Virgo constellation. The principle is quite simple. When the exoplanet passes in front of its star, the light from the star will pass through its atmosphere. Scientists will then be able to study the spectrum of the light, in particular, the absorption lines, which are sort of holes caused by the gases that the light has passed through before reaching us. Each gas has its own absorption lines. Just by studying the spectrum of light from K218 passing through the atmosphere of K218b, astrophysicists will be able to determine which gases are present and in what proportions in the atmosphere of this exoplanet. In any case, the exoplanet K218b is considered by many astronomers as one of the most promising exoplanets for the existence of an extraterrestrial life form, although it is more than 1 billion million kilometers and a half away from Earth. Before diving into the heart of this planet, let's review the criteria that a planet must meet, according to scientists, to be likely to host life. For decades, scientists have limited themselves to our solar system. The search for life on Mars or Venus was the subject of many observations and space explorations. In the 1990s, the question of the existence of extraterrestrial life was revived with the discovery of exoplanets. Exoplanets are, I remind you, planets that orbit other stars than the Sun. They are, in short, all the planets except those of our solar system, namely Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. There are billions of exoplanets in the universe, which are very far from our Earth. The possibility of extraterrestrial life somewhere in the universe is therefore stronger than ever. Since the discovery of exoplanets, scientists have been trying to find another Earth, or at least an exoplanet that would meet all the conditions for the development of life. These criteria were modeled on what we know, the development of life on Earth. For an exoplanet to be a potential candidate for the search for extraterrestrial life, it must first be rocky like the Earth, and not gaseous like Jupiter. It must have water in liquid form on its surface, since water is the basis of life. Why in liquid form? Because liquid water allows molecules to meet and interact to create life. This is not the case with frozen water, for example. Finding an exoplanet that harbors water in liquid form is not so easy. This planet must have a mass close to that of the Earth. If it is too massive, its gravity will attract all the surrounding gases, and we will have a gaseous planet. This is why the most massive planets in our solar system, Jupiter, Saturn, Uranus, and Neptune, are gaseous and not rocky. But if we are in the presence of an exoplanet that is not massive enough, its gravity will be too weak to retain its atmosphere. However, the presence of an atmosphere is another criterion for the development of life. Without an atmosphere, water in liquid form would evaporate instantly. For an exoplanet to harbor water in liquid form, it must also have a moderate surface temperature. This means that it must be neither too hot, otherwise the water would evaporate, nor too cold, otherwise the water would freeze. It must therefore be in what astronomers call the habitable zone of its star, i.e., the zone where the temperature allows the presence of water in liquid form. K218b is indeed located in the habitable zone of its star, neither too close nor too far. Earlier in this trip, we talked about its equilibrium temperature, which is minus 23 degrees Celsius, or minus 9.4 degrees Fahrenheit. This is very close to the Earth's equilibrium temperature of minus 18 degrees Celsius, or minus 0.4 degrees Fahrenheit. In practical terms, K2-18b orbits closer to its star than we do to the Sun. But let's not forget that its star is a red dwarf, smaller and colder than our Sun, which is a yellow dwarf. K2-18b receives about the same amount of energy as we receive from the Sun. According to the analyses, it would receive about 1,500 watts per square meters, while we receive from the Sun 1,370 watts per square meters. However, scientists do not get carried away. It is not because K2-18b is located in the habitable zone of its star that it is necessarily inhabited. The appearance of life on Earth was the result of multiple factors, not only of a favorable temperature. It is possible that K2-18b harbors living single-celled microbes and bacteria, but depending on the composition of its atmosphere, it may not be able to harbor more complex creatures. This has been established for many exoplanets that have been discovered. They were located at the right distance from their star, in the habitable zone, but their atmosphere saturated with toxic gases makes them unsuitable for the emergence of complex life. What convinced scientists that K2-18b could prove interesting for the search for alien life was the discovery of water vapor on this exoplanet in 2019. Two independent studies, combining data from the Kepler, Hubble, and Spitzer telescopes, have concluded that the atmosphere of K2-18b contains significant amounts of water vapor, which is unprecedented for an exoplanet located in the habitable zone of its star. In other words, this is the first exoplanet found that combines being in the habitable zone of its star with evidence in its atmosphere of liquid water. How did scientists discover water vapor in the atmosphere of an exoplanet located more than 100 light-years from our planet? The first team used data from the Hubble telescope's wide field camera and used an algorithm to process the data. They identified the molecular signature of water in the atmosphere of K2-18b. The second team used data acquired during 3 years by the Hubble, Spitzer, and Kepler satellites to analyze 8 transits of K2-18b in front of its star. In particular, they observed the spectra of the starlight passing through the atmosphere of the planet during these 8 transits. They found that the atmosphere of K2-18b is rich in hydrogen and helium, with a high concentration of water vapor, probably between 20% and 50%. According to astrophysicists, detecting water molecules is very common on gas giants like Jupiter, but rarer in the atmosphere of rocky planets like Earth, especially when they are in the habitable zone. Until now, scientists had only deduced from numerical models the presence of water molecules in the atmosphere of Proxima b, which orbits Proxima Centauri, the closest star to the Sun that we observed on our way here earlier. And that's it. The direct detection of water molecules in the atmosphere of the rocky exoplanet K2-18b is thus a new fact, especially since it is quite possible that the detected water could form rain droplets or even an ocean on the surface of K2-18b. As a reminder, water had already been detected in exoplanets, but they were not in the habitable zone. This is the case, for example, of HD 209458b, WASP-12b, WASP-17b, and WASP-19b. The astrophysicists recalled that the presence of water in the atmosphere of K2-18b does not necessarily mean that it is inhabited or even habitable. Many questions still remain, including how much water vapor is present in the atmosphere, and whether it is accompanied by traces of organic chemistry, such as oxygen and ozone. All that is known is that, like Earth and Venus, K2-18b is probably composed of silicates as a rocky planet, and that water may not be present in liquid form, but as ice. Scientists expect a lot from the observation of K2-18b with the James Webb Space Telescope, launched in December 2021. More powerful than Hubble, it will perhaps be able to tell us more about the precise composition of the atmosphere of K2-18b. If these discoveries have excited a large part of the scientific community, there are still some gray areas. First of all, K2-18b is between 6 and 10 times the mass of the Earth, with a radius of 2.3 that of the Earth. With this radius, its density seems far too low to be a rocky planet. If K2-18b is indeed rocky, then it would be composed largely of so-called volatile constituents, which would form a fluid envelope, such as molecular hydrogen, helium, and water. This is why K2-18b is often referred to as mini-Neptune. Indeed, Neptune has no solid surface. It is in fact composed of a solid core covered by a warm and dense layer of water and liquid ammonia, and its atmosphere is made of hydrogen and helium. In addition, for water to be present in liquid form on K2-18b, other factors would have to be present. The presence of water molecules in the atmosphere of the exoplanet does not mean that it is present in liquid form. It could very well be in the form of ice. To be sure that the water present on the surface of K2-18b is indeed liquid, it would be necessary to verify the water content of the planet, the composition of the atmosphere, the rotation of the planet, the existence or not of a solid surface. We still don't know if K2-18b looks like a super-Earth or a mini-Neptune, which would be inhospitable. Some scenarios even make it an ocean planet with liquid water under the atmosphere and temperature and pressure conditions close to those of our oceans on Earth. There is one more thing. Is K2-18b really located in the habitable zone of its star? We tend to rely on what we know. So by comparing K2-18b and the Earth, especially their equilibrium temperatures, it seems that yes. But let's not forget that K2-18 is a red dwarf, very different from the Sun, which is a yellow dwarf. The spectrum of K2-18 is more efficient to heat an atmosphere than that of the Sun. If we were to place the Earth at the same location as K2-18b, it is likely that the oceans would evaporate. Instead of reflecting 30% of the incident energy, the Earth would reflect only 10%. For K2-18b to be habitable, it would have to rotate synchronously with its star, i.e., it would always show the same face to K2-18, which would allow thick clouds to form on the exposed half. This would give a habitable climate. These questions are still being studied by astrophysicists, who are waiting for more powerful telescopes like James Webb to confirm or refute their hypotheses. The observations of James Webb could also enlighten us on the difference between methane and water vapor, which remains unclear. Recently, a study conducted by Lesia researchers has shown that the absorption observed by Hubble during the 8 transits of the planet in front of its star could in fact be due to methane. Methane is found in abundance in the atmosphere of temperate mini-Neptunes. Methane is certainly less abundant than water vapor, but the two can be easily confused. The instruments on board James Webb will probably be able to tell us more. Let's assume that K2-18b is indeed home to life. You wonder then what life would be like on this planet located thousands of billions of kilometers away and miles from us. The notion of a habitable zone remains very relative. By definition, it is, as you know, the distance at which a planet, in relation to its star, could potentially harbor liquid water on its surface. The distance varies according to the radiation of the star. For a red dwarf, the zone of habitability is closer than for a yellow dwarf like the Sun, because a red dwarf is colder, smaller, and less luminous than a yellow dwarf. K2-18b is thus located closer to its star than we are to the Sun. Given this proximity, there is a strong chance that K2-18b is in synchronous rotation with its star. On this planet, there would be no nights or seasons. Living beings would be grouped on the day side, the one that is always facing the Sun, while the night side, too cold, would be uninhabited. The red dwarf, as its name indicates, emits a red radiation, unlike our Sun, which emits a yellow radiation. The living beings on K2-18b would thus see in the sky a red star, with a disk certainly larger than the solar disk, since K2-18b is closer to its star than we are to the Sun. The gravity on K2-18b is 37% greater than on Earth. Thus, the development of life on this planet would have adapted to this stronger gravity, giving forms of plants and animals much more imposing than what we can know here on Earth. The living beings would have more strength compared to us, and would need more energy to feed themselves. Obviously, we would not find the same plants on this planet. Studies have shown that plants are indeed sensitive to red light because they have a photoreceptor for red light, a blue-green pigment called phytochrome, which is found in plant cells. Plants grown under red light are larger and taller, with many branches. Red light could also influence the color and flavor of plants. Instead of being green, K2-18b plants would be black in order to better absorb light from the K2-18 star. Red dwarfs are known for their frequent violent eruptions. The Sun also has eruptions, but much less violent than that of red dwarfs. We are also protected by the Earth's magnetic field. On the other hand, the eruptions of red dwarfs would be capable of tearing the atmosphere of the planets around, especially since habitable planets around red dwarfs are much closer to their star than habitable planets around a yellow dwarf like Earth. So even flares similar to those of our Sun could affect planets like K2-18b more. The researchers then wondered if, because of these frequent flares, exoplanets around red dwarfs might be too hostile for the development of life. Not only could a single eruption of the red dwarf K2-18 damage the atmosphere of K2-18b, but also, according to some researchers, there could be a cumulative effect. In other words, the more eruptions there would be, the more the atmosphere would be torn apart. Thus, even the weak eruptions, which seem to be the most frequent, would present a danger. However, it all depends on the composition of the atmosphere, which scientists have not yet been able to determine precisely with respect to K2-18b. It could thus be difficult to find habitable land around red dwarfs. Indeed, a planet of mass equivalent to ours or higher has great chances to keep throughout its evolution because of its gravity, a thick atmosphere. Also, in these conditions where the greenhouse effect is enormous, the possibility that water could remain in a liquid state evaporates. But all is not lost. For researchers, the conditions for a form of life would be more favorable on the surface of worlds less massive than the Earth. Planets similar to Mars, called exomars, which do not retain their atmosphere well, could be good candidates. The good news is that these small balls of rock are probably much more numerous than the larger, more massive planets. If life were possible on K2-18b, the life expectancy of a species could be much greater than that of species on Earth. Because red dwarfs evolve very slowly, much slower than our Sun, which will eventually turn into a red giant, swallowing the Earth in about 5 billion years. A red dwarf, therefore, leaves much more time than a yellow dwarf for life to develop on the planets that orbit it. At the moment, the latest data suggests that water vapor makes up between 0.01% and 50% of the atmosphere of K2-18b. With such a large range, it is difficult to characterize the exoplanet. It could be completely covered with water, or on the contrary, be a world similar to ours, with lakes and oceans with many exposed lands. What if K2-18b was an ocean planet? If so, the planet would be home to aquatic species, surely different from those found in our oceans. This extraterrestrial ocean could be deep and dense in such a way that even at high temperatures, the pressure would turn the deep water into ice. The immense pressures in these deep ocean regions could lead to the formation of a mantle of exotic ice forms. This ice would not necessarily be as cold as conventional ice. If the planet is close enough to its star, as is the case with K2-18b, and the temperature and pressure at its surface are high enough for the water to reach its boiling point, the water would become a supercritical fluid and would not have a well-defined surface. But according to the latest data, the surface temperature on this planet is between minus 73 degrees Celsius and plus 47 degrees Celsius, i.e., between minus 99.4 degrees Fahrenheit and plus 116.6 degrees Fahrenheit. Even if the temperature is still uncertain, it is not high enough for the water to reach the boiling point. If K2-18b is indeed dominated by water, the atmosphere may be much thicker than Earth's and composed largely of water vapor, producing a very strong greenhouse effect. The problem? Such a planet would have to be small enough not to be able to hold a too thick envelope of hydrogen and helium. Otherwise, they would rather form a hotter version of an ice giant, like Uranus and Neptune, making any form of life impossible. However, K2-18b is a super-Earth and could very well have evolved as a hot Neptune. But its proximity to its central star could save it. Indeed, as K2-18b is close enough to its Sun, it could be stripped of its light elements by the solar flares of the red dwarf, thus preventing the formation of a thick atmosphere. So there could well be stable oceans on K2-18b. Even if the oceans of K2-18b are of different composition than ours, this does not mean that life would be impossible there. On the contrary, it would simply be another form of life. We have found organisms on Earth that are capable of developing in the Dead Sea. The tardigrade is a good example of an ultra-resistant animal species. 1,000 tardigrades were sent to the moon via a space probe in 2019, and since then these animals have survived perfectly well in this inhospitable environment. The tardigrade is an animal with 8 legs, which measures only 1 millimeter, and which can resist to extreme environments. It survives temperatures between -273 degrees Celsius and +340 degrees Celsius, i.e., between -460 degrees Fahrenheit and 644 degrees Fahrenheit. It is 11,000 times more resistant than humankind to X-rays. It survives pressures 4 times higher than the pressure of the deepest part of the ocean, but also the lack of oxygen, dehydration, alcohol, toxic products. In addition, it can reproduce alone. To adapt in this way to such extreme environments, it changes its mode of functioning, and in particular, resorts to cryptobiosis, a state in which it is almost dead. It curls up, it empties itself of its water, which it replaces with a sugar, and it reduces its metabolic process to 0.01% of normal. It can rehydrate and wake up decades later. Outside of cryptobiosis, its lifespan is 1 to 3 years. We could therefore find ultra-resistant animals on K2-18b, whether it is an ocean planet or a rocky planet, which would resist solar flares, and perhaps even the temperatures and lack of luminosity of the night part. The example of the tardigrade shows that we should not underestimate the capacities of animal species. Now, let's suppose that K2-18b could harbor life and that there are aliens on this exoplanet. After all, why not? And if so, could we communicate with them? The participatory project, Stahaya Beyond, which was born in Uzbekistan, aims to send musical tracks to extraterrestrials. The goal is to transform a selection of local and international music into binary code so that it can be sent into space via a UK satellite radio station in order to reach K2-18b, the best candidate to date for the presence of extraterrestrial life. However, although K2-18b is not the most distant exoplanet from us, it would take 124 years for the extraterrestrials to receive the message. The earliest we could get an answer would be 248 years. This project is an opportunity to ask many questions. What will we do if we come into contact with the extraterrestrials? How will we communicate? And especially, how will we understand each other, since they will not speak our language? This also brings us back to the question, are we alone in the universe? A question that astronomers have been asking for centuries, and to which we are not close to finding an answer. The Andromeda Galaxy, with its 1,000 billion stars, is often considered the twin sister of our Milky Way. Measuring 220,000 light-years in diameter, Messier 31 is a huge celestial object, the furthest from Earth that can be observed with a naked eye under clear skies, even though it is 2.5 million light-years away. The first observations of this luminous spot go back to the dawn of time, but the first written records date back to 964. They are due to Al-Sofi, a Persian astronomer. The Andromeda Galaxy, located in the constellation of the same name, is easily recognized by its oval and diffuse shape with a bright core. The latter, of yellow color, contrasts with the dark dust bands and the large arms that trace their way around. This is a spiral galaxy, the closest to our galaxy, which offers us a breathtaking spectacle. In its meanders, we can see clusters of blue stars, but also nebulae of reddish color. The total mass of the Andromeda Galaxy, estimated at 1,230 billion solar masses, against 1,900 billion solar masses for the Milky Way, does not prevent it from containing a considerable number of stars more. In the heart of its bowels is a supermassive black hole, estimated at 140 million solar masses, which is much larger than the one in our galaxy, which is estimated at only 4 million solar masses. Andromeda has two companions, Messier 32 and Messier 110, both of much smaller size. The first, Messier 32, is a compact elliptical galaxy, its greatest length not exceeding 8,000 light-years. Distant from the Sun by 2.5 million light-years, it is an elliptical dwarf galaxy with a mass of only 3 billion solar masses. Although it may seem insignificant, it contains a central bulge whose characteristics are comparable to that of its host, M31, with a mass of about 100 million solar masses. It is estimated that approximately 5,000 stars per cubit parsec are rapidly rotating around a central supermassive object. It is mostly composed of old stars and has a high surface brightness. All indications are that Messier 32 was once much larger, but that its outer star population and globular clusters were considerably absorbed by its giant host, the Andromeda Galaxy. But what about this giant second companion, Messier 110? Is it as impacted by its proximity to the Andromeda Galaxy? Like Messier 32, it is an elliptical dwarf galaxy, which does not appear to contain a supermassive black hole. Its diameter is 17,000 light-years, twice that of Messier 32. It is smooth and almost featureless, with no arms or star-forming regions, but it does contain a population of young blue stars in its center. There are 10 billion of them, as well as 8 globular clusters that are visible in its halo. As you can see, Messier 110, unlike its companion, does not appear to be at the end of its activity. These three cosmic monsters are far from evolving alone. The Andromeda Galaxy and its two smaller sisters are accompanied in their astral dance by many smaller galaxies. These form the subgroup of Andromeda. There are at least 14 dwarf galaxies that belong to the Andromeda Galaxy subgroup. Of course, there is Messier 32 and Messier 110, whose discoveries date back to the 18th century. But since the 1970s, new galactic objects have been discovered, one after the other, thanks to technological advances. Thus, the galaxies Andromeda 1, 2, and 3, all distant between 2.1 and 2.4 million light-years from our Sun, were discovered in 1972 by Sidney Vandenberg, a Canadian astronomer. This scientist also discovered Andromeda 4 at the same time. If he believed at first that it was an irregular galaxy belonging to the subgroup of Andromeda, the measurements made in 2000 with the Hubble Space Telescope place it rather between 16 and 26 million light-years. This galaxy would then be largely outside the local group. In 1998, the galaxy Andromeda 5 joined the subgroup of spherical dwarf galaxies of Andromeda. It is 2.6 million light-years away from our solar system. Also in 1998, it was the turn of the spheroidal dwarf galaxy of Pegasus, or Andromeda 6, and the dwarf galaxy of Cassiopeia, Andromeda 7, to be revealed. The distance of the former is still poorly defined, but it could be between 2.5 and 3.1 million light-years, while the latter is estimated at 2.5 million light-years. We will not continue this list, which extends to Andromeda 33, a dwarf galaxy of the same type as its consorts and discovered in 2013 thanks to the Pan-STARRS-1 astronomical survey program that uses a panoramic survey telescope and rapid response system located on the Hawaiian archipelago. Among the main members of the local group, other cosmic monsters, although less imposing, are just as marvelous and reserve us an extraordinary show. This is notably the case of a duo of dwarf galaxies, separated by only 75,000 light-years. These are the famous Magellanic Clouds. These two galaxies, very close to our galaxy, are remarkably visible to the naked eye from the southern hemisphere, appearing as two milky spots in the deep sky and resembling fragments of a cloud of stars that would have broken away from our galaxy. It is not known when the first observations of these two celestial objects date back to, but it is in 924 that the Large Magellanic Cloud is described for the first time in the literature by the Persian astronomer al-Sufi, even if their identification was formalized during the voyage of Ferdinand Magellan in the 16th century. But what makes these two galaxies even more curious is a kind of bridge that seems to connect them to each other. Let's get a little closer to this strangeness. Let's start by observing the Large Magellanic Cloud, which is a dwarf galaxy of the barred spiral type. It is located in the constellations of the Dorado and the Table. Its disk shape is characterized by the presence of a single spiral arm and a large bar that were discovered long after the galaxy itself, which explains why it was first catalogued as an irregular galaxy. The Large Magellanic Cloud is 163,000 light-years distant from our solar system. But more importantly, it occupies the 4e position in the local group in terms of mass, after the Andromeda Galaxy, the Milky Way, and the Triangulum Galaxy. Several 100,000 giant and supergiant stars are counted there, as well as 60 globular clusters, 400 planetary nebulae, and 700 open clusters. Among the very many celestial objects it contains, we can note two high-mass stellar black holes, both in the form of binary systems. We can also observe a soft gamma-ray booster, the first object of this type to be discovered. It is a source of gamma rays with violent and recurrent episodes of emission, but regular and most probably corresponding to young neutron stars with intense magnetic field. One of the youngest pulsars, probably about 1,650 years old, with a rotation period of 50.3 milliseconds, can also be seen. These last two objects are both located in the aftermath of supernovas, these explosions of stars that give us a show of beauty. We can thus see that an intense activity reigns in the interstellar median of the Large Magellanic Cloud, where the quantities of gas and dust are colossal. This explains why an important quantity of new stars emerge in its heart. The largest and most active region of the local group is the Tarantula Nebula. This galaxy is the most active of any region in our galaxy and has a star birth rate like no other. In fact, The Tarantula Nebula is the largest nebula known to date. But what makes the Large Magellanic Cloud so special is the link it has with its fellow traveler. Indeed, the southern bar of the Large Magellanic Cloud is connected to the Small Magellanic Cloud by a bridge of gas and stars, known as the Magellanic Bridge. This structure, which is due to the tidal forces linking the Magellanic Clouds, and perhaps also to those of the Milky Way, is mainly composed of neutral hydrogen. However, it is home to a few stars that must have formed within it. The Small Magellanic Cloud is an ancient barred dwarf spiral galaxy, which has become an irregular galaxy due to the inexorable tidal forces around it. Distant from our Sun by about 200,000 light-years, its diameter is half that of its big brother, reaching 7,000 light-years. For those who have the opportunity to observe it from the southern hemisphere, it occupies in the night sky the value of 10 full moons, which made it, in the first Polynesian or Australian Aboriginal cultures, an indispensable tool for navigators. This visibility, to the naked eye, is mainly due to its small distance from our Sun, although it is one of the most distant objects that can be observed without instruments. If the Small Magellanic Cloud is considered small compared to other galaxies, it would nevertheless contain no less than 3 billion stars. We can also admire in the heart of this small galaxy many objects all more luminous and colorful than the others, including star clusters that shine brightly, supernova remnants, or magnificent nebulae, where the occurrence of new stars is particularly intense. Let's move on to the third galaxy of the local group, the Triangulum galaxy, also known as Messier 33, which lies in the northern constellation of Triangulum. Located about 2.7 million light-years from Earth, it is over 50,000 light-years in diameter and hosts more than 40 billion stars. It is a regular spiral galaxy, which means that it is unbarred. Without rings, it is in the form of a galactic disk that surrounds a central bulge. The mass of this galactic monster is estimated at 60 billion solar masses, which is still far less than our Milky Way and the Andromeda galaxy, which are both at the top of the podium in terms of size. Messier 33 represents only 5% of the mass of the Andromeda galaxy, estimated at 1,230 billion solar masses. The Triangulum galaxy is very different from the Milky Way, which you have certainly visited. It is larger, flatter, and brighter. It also has a large number of spiral arms, rather open, each containing billions of stars and gas clouds. The absence of significant interaction of this galaxy with other massive objects allows it to maintain its beautiful spiral structure, a relatively symmetrical overall shape, and therefore does not experience major alterations. Like its larger sisters, it has a large amount of gas and dust, which makes it an ideal place for the formation of stars and planets. As you travel through the Triangulum galaxy, you can see many types of stars, including red dwarfs, red giants, binary stars, and massive stars. In fact, astronomers count more than 500 active regions of infrared radiation that are massively concentrated in its center and along its spiral arms. Among the brightest regions of the galaxy are its main nebulae, NGC 588, NGC 592, NGC 595, and NGC 604. The latter, also called the Triangle Nebula, is the brightest of all and extends over nearly 1,500 light-years. It is the second most luminous region of ionized hydrogen in the local group. Thanks to the Hubble telescope, we know that it hosts about 200 young and hot stars distributed in at least 2 clusters. Their masses vary between 15 and 60 solar masses. Moreover, it is in the southern spiral arm that the rate of explosion of supernovas is the most important. There would be, on average, every 147 years, which explains the 100 of supernova remnants that could be identified there. There are also many other interesting phenomena, such as jets of matter, expelled by some supermassive black holes. In summary, the Triangulum galaxy is a place full of discoveries and wonders of nature. It's an incredible sight to see, isn't it? Among the main members of the local group, I invite you to discover now NGC 185 and NGC 147, 2 galaxies that belong to the great majority that compose the local group, namely the dwarf spheroidal galaxies. However, as you will see, these 2 dwarf galaxies have a small peculiarity, apart from belonging to the Andromeda subgroup. Let's start with NGC 185, a dwarf spheroidal galaxy located about 2.1 million light-years from our Sun. It is remarkable for its small size and low mass, which is approximately 1/10 that of the Milky Way. If, like all galaxies of this type, it contains few stars and gas because of its advanced age, on the other hand, its surface, of a very high luminosity, and its extremely bright and compact nucleus place it in the category of Seyfert galaxies of Type 2. This type of nucleus represents one of the largest known sources of electromagnetic radiation in the universe. Would it hide a supermassive black hole in its center? Therefore, it arouses our curiosity, especially since it displays a notable proximity to a neighboring galaxy, NGC 147. Like its companion, NGC 147 is a dwarf spheroidal galaxy, located about 2.2 million light-years from our solar system. It also contains few stars and gas, but what makes it intriguing is its particular location near its neighbor. It seems that these 2 galaxies form a gravitationally stable binary system. These galaxies may not look as impressive as the large spiral galaxies, but they are interesting to study because of their interaction and proximity, especially since a third object, the recently discovered pale dwarf galaxy, Cassiopeia II, may also be part of this satellite system of the Andromeda galaxy. It may well be that these 3 galactic objects are part of the same cosmic dance. But to confirm this, we will have to examine their choreography for some time. Let's continue our exciting journey through the Barnard Galaxy. This galaxy is shyly located in the constellation of Sagittarius, about 1.5 million light-years from the Milky Way. It hides its irregular shape behind a screen of dust and closer stars, which explains why it was only discovered in the 1880s by Edward Emerson Barnard. Its appearance is not unlike that of the small Magellanic Cloud, is it not? Its largest diameter reaches 7,000 light-years, and although it does not shine like the biggest divas of the local group, it is full of young blue stars. Although it does not have splendid spiral arms, it is surrounded by a necklace of purple nebulae, where intense activity heats the surrounding hydrogen during star formation. As a proof, we can sometimes see a brood of massive stars that ejects with an unheard-of violence the matter, literally blowing the interstellar gas. This small galaxy has nothing to envy to the larger ones, showing signs of an obvious star formation activity. Let's visit the last of the main members of the local group, the galaxy named IC 1613. Located in the constellation of Cetus, the sea monster, and distant a little more than 2.3 million light-years from our Sun, we owe its discovery to the German astronomer Max Wolf in 1906. But it was in 1928, using a powerful 2.5-meter or 8-foot telescope at the Mount Wilson Observatory, that his compatriot, Alter Bod, successfully visualized its individual stars. Once again, this is a dwarf galaxy with low surface brightness. But our journey to it is not by chance. This galactic neighbor, unlike its fellow galaxies, has made a clean sweep. What we want to explain to you is that it contains very little cosmic dust, allowing it to reveal the wonders it contains. This phenomenon is quite rare, and therefore worth observing. No dark trail of sidereal dust, opaque and swirling, is visible among the gas and stars that populate this galaxy, which appears clean as a whistle. Two types of stars can be seen, pulsating at their own pace: Cepheid variables and RR Lyrae variables. Because of its unusual appearance, the IC 1613 galaxy offers great opportunities for observations. Despite its small size, it has helped scientists to understand and use variable stars to map our universe. So it is not the largest objects that hold all the keys to the cosmos. I now propose you to visit the dwarf spheroidal galaxies which compose the subgroup of the Milky Way, and to which they are gravitationally linked. They can be observed in this small corner of the universe, within a radius of 1.5 million light-years around our galaxy. Let's start with a huge galaxy that has been hidden for a long time behind the galactic disk of the Milky Way, in the constellation of Antlia, at a distance of 422,000 light-years. Its existence was detected in 2018 by the Gaia satellite. Let me introduce you to the Antlia II galaxy. This galaxy, with nearly 9,500 light-years in diameter, is relatively similar to the Large Magellanic Cloud, but unlike the latter, its brightness is 10,000 times less. It even appears 100 times more diffuse than the so-called ultra-diffuse galaxies, whose luminosity is very low, making it the least luminous of all the galaxies known to date. This characteristic is also the reason why it is called a ghost galaxy, although its size is 1/3 of that of the Milky Way. In short, it is a galaxy that is either too dark for its size or too large for its brightness. One of the most interesting features of Antlia II is that it is also rich in dust clouds, which are regions where new stars and planets form. These dust clouds are visible due to their absorption of light from the background stars, forming dark regions called dark dust clouds. Antlia II is rich in young stars and gas. This means that there are many new stars forming in this galaxy. In fact, it is estimated to be about 10 times more active in star formation than the Milky Way. Therefore, as you can see, there are many star clusters in Antlia II. These clusters are groups of thousands of stars that have formed together from a single cloud of gas. Some of these clusters are very young, and still contains stars in the process of forming. Another particularity is noteworthy. Its mass appears well below the first estimates made on the basis of its size. Could it be the consequence of incessant dismantling caused by the galactic tides of the Milky Way? Moreover, this galaxy, whose age is about 11.2 billion years, raises another problem for scientists: a problem of size. In theory, galaxies that are devoured by another galactic monster see their size reduced. Antlia 2 is huge and seems to be growing rather than shrinking. It seems that this phantom galaxy has not yet revealed all its secrets, which makes it even more fascinating. Another galaxy is the talk of the scientific community. It is the Sagittarius Dwarf galaxy, which has been the subject of debate since its discovery in 1994. It is considered by some as a spheroidal galaxy and by others as an elliptical galaxy. Be careful not to confuse it with the irregular dwarf galaxy of Sagittarius. About 10,000 light-years in diameter, it is approximately 50,000 light-years from the center of the Milky Way, which makes it also one of its satellites. Its population of old and metal-poor stars makes it possible to establish that it is an old galaxy, especially since it has little interstellar dust. We can think that it was at the base of a dwarf spheroidal galaxy, which would have suffered the consequences caused by tidal forces of the Milky Way, especially since a significant number of its stars and a stream of gas appear scattered throughout its orbit. Moreover, the dwarf galaxy of Sagittarius seems to disturb intermittently the outer disk of the Milky Way, to which it is a little too close since 5 or 6 billion years, producing numerous filamentary structures. If at the moment of these structures of filamentary and spinning appearance are not yet explained by astronomers, several theories are emerging. In particular, that of the remains of fossil spiral arms. Whatever the case, these structures are certainly related to past interactions with the Milky Way. The interactions between the Sagittarius dwarf galaxy and our galaxy are not going to get any better, since its trajectory indicates that it should cross the Milky Way galactic disk within 100 million years. It will thus probably be absorbed entirely by our galaxy through a long process of destruction and restructuring. In the category of spheroidal dwarfs, we can continue our journey towards the Dragon dwarf galaxy. Located in the constellation of the Dragon, at about 260,000 light-years from the Earth. Its discovery dates back to 1954 by Albert George Wilson of the Lowell Observatory. It is globular in shape and extends from 2,700 to 1,800 light-years, making it one of the smallest galaxies known. It is also very faint in terms of luminosity. It is one of the least luminous companions of our galaxy. This object that orbits our galaxy also seems to contain large amounts of dark matter. This mysterious matter, still hypothetical, and whose existence has not yet been proven directly. It has thus become an ideal candidate for the scattering phenomenon and could be very useful for scientists working to understand cosmic mechanisms. However, more than 260 variable stars accumulate at its center, and despite its small size and luminosity, the Dragon dwarf galaxy is rich in old stars and metals such as iron, calcium, and magnesium. The ancient stars probably formed billions of years ago. The presence of these old stars and metals indicates that the Dragon Dwarf galaxy has experienced a lot of star formation activity in the past. It also contains several red giants, which are low luminosity stars. These stars have exhausted their nuclear fuel and consequently have stopped shining. These stars are very enriching because they contain information about the history of the galaxy. They are also potential candidates for the search for extrasolar planets. Who knows, maybe one day we will be able to detect the presence of potentially habitable planets in this region of the cosmos. Among other deep sky objects, we can also explore the dwarf galaxy of the Little Dipper, which can be reached in the constellation of the same name. Its average distance from our Sun is 205,000 light-years, while it is only 1.4 million light-years from the center of the local group. Its size, 45 times smaller than the Milky Way, is estimated at 2,200 light-years. Discovered under the same conditions as the Dragon Dwarf galaxy, the findings seem identical. It is similarly a galaxy that could contain a large amount of dark matter. Indeed, the velocity dispersion does not decrease with the distance to the center of the galaxy. Moreover, 94 bright stars have already been identified in the bowels of this object, whose radial velocity brings it closer to our solar system at a speed of 247 kilometers per second, or 153 miles per second. This is a new galaxy with many suns, which seems to be expanding. Do you think that it may have a few planets where extraterrestrial life could have developed? And why not? But do you know which is the first dwarf galaxy that was discovered orbiting the Milky Way? Well, it's the Sculptor Dwarf galaxy, first described in 1937 by astronomer Harlow Shapley. Since then, many other observations have been made, notably thanks to the Gaia study of the European Space Agency and observations made with the Hubble Space Telescope. The galaxy has, among other things, allowed scientists to determine how individual stars move through a galaxy of this type. They are now able to confirm that their change in position is tiny, even over long reference periods of about 10 years. The proper motions of about 100 stars have been measured, and coupled with the radial velocity, the motion of the stars could be reconstructed in 3 dimensions. This is the first time that such a reconstruction could be performed for a dwarf galaxy. The Sculptor Dwarf galaxy thus plays a crucial role in the astronomer's sphere, who can now study the impact that the gravity of dark matter, this elusive matter, can have on the motion of other objects, such as stars or galaxies. Let's now take the direction of the Sextant constellation, where the 9th satellite of the Milky Way is hidden, the Sextant Dwarf galaxy, or Sextans 1. This galaxy, of spheroidal type, was detected in 1990 by Mike Irwin as part of a comprehensive sky survey plate monitoring program, United Kingdom Schmidt Telescope, with the application Performance Monitoring Measurement Machine in Cambridge, UK. The distance of this object is estimated to be only 280,000 light-years from the Sun. Its apparent magnitude is 10.4, which makes it one of the least luminous galaxies among the closest to our Milky Way. As you can see, it is also an elliptical galaxy, With a redshift as it moves away from us at a constant speed of 224 kilometers per second, or 140 miles per second. It is small, and its diameter measured along its main axis does not exceed 8,400 light-years. As you can see, its population consists of old stars poor in metals. The in-depth study of this galaxy allows us to question the hierarchical formation scenario. This theory, according to which galactic monsters such as our Milky Way would have been created mainly by absorbing other galactic objects over time, cannot be affirmed when we study more closely the chemical composition of the dwarf galaxies that surround it. Indeed, compared to our galaxy, Sextans 1 presents a deficit of the most primitive stars. This indicates that the fossil content of the primitive epochs, the epoch that precedes the assembly of galaxies between them, is not similar. Thus, neighboring dwarf galaxies do not have the same characteristics as the halo of our Milky Way, its oldest part. Moreover, the Sextant 1 galaxy, like many other galaxies of the same type, lacks very low iron stars, unlike our galactic halo. Here is another dwarf spheroidal galaxy, the Carina dwarf galaxy, also named PGC 19441. It is found in the constellation Carina. This satellite of the Milky Way is about 330,000 light-years away, but is gradually moving away at a speed of 230 kilometers per second, or 140 miles per second. Its size is estimated to be 75 times smaller than our galaxy, with a diameter of 1,600 light-years. It is part with the Lion 2 galaxy of the smallest known galaxies. It is home to a majority of stars whose formation dates back approximately 7 billion years, which means that they appear less ancient than those of other satellite galaxies. The Carina dwarf galaxy may be more recent than its twin galaxies, although it has also experienced other peaks of star formation, notably 13 and 3 billion years ago. Another satellite galaxy of the Milky Way attracts our curiosity, this time in the constellation of the Furnace. It is the dwarf galaxy of the Furnace. Distant from 450,000 light-years from the Sun, it is, like almost all nearby dwarf galaxies, composed mostly of old stars, called Population 2. It has a recession of 53 kilometers per second, or 33 miles per second, moving further and further away from our Milky Way. Its low surface brightness makes it unattractive at first sight. However, it contains several treasures, including a planetary nebula and 5 globular clusters, the largest of which, named NGC 1049, was discovered a century before its host by the British astronomer John Herschel in 1835. This cluster contains a large number of stars, which makes it brighter than the galaxy itself. As proof, its distance of 444,000 light-years does not make it invisible with a medium-sized telescope, unlike the galaxy that hosts it. This cluster and its companions have been the subject of numerous observations. It appears that they are very similar to those existing in our Milky Way. This observation challenges the main theories on the formation of these clusters, which should be surrounded by large quantities of old stars. However, we see that this is not the case here. As is often the case in astronomy, A new observation, even if it opens a little more the door of our knowledge, puts in question some theories, leading to new questions. Let's now look at the last two spheroidal dwarf galaxies belonging to the Milky Way subgroup, the Leo 1 galaxy and its twin, the Leo 2 galaxy, also named Leo 1 and Leo 2. Their simultaneous discovery is attributed to Robert Georges Harrington and Albert Georges Wilson in 1950. Like the Carina galaxy, their diameter does not exceed 1,600 light-years, which makes them the smallest known galaxies of the Milky Way subgroup. The first, the Leo 1 galaxy, is 800,000 light-years away from our Sun. The second, slightly closer, is 700,000 light-years away. The latter is made up of stars 8 billion years old. It does not produce any more new stars, except in the center, where we can see younger stars. Leo 1, however, has captured the attention of researchers since it was found that it contains a relatively small amount of dark matter compared to its peers. It was in 2021 at the McDonald Observatory, and with the help of a supercomputer, that a team from the University of Texas discovered that a supermassive black hole, namely of 3.3 million solar masses, reigns at the heart of the Leo 1 galaxy. Here is yet another mystery to be solved. How can a black hole of this mass exist in such a small galaxy? We have just visited the dwarf spheroidal galaxies belonging to the Milky Way subgroup. However, there are other dwarf spheroidal galaxies that are labeled as ultra-faint. If you want, let's go to meet them, while staying in the constellation of Leo. The discoveries follow one another thanks to new technologies and numerous programs. The Sloan Digital Sky Survey, or SDSS for short, is a celestial object survey program using a dedicated 2.5-meter or 8 feet diameter optical telescope located at the Apache Point Observatory in southern New Mexico, USA. This program, which started in 2000, has allowed to count in 2006 about 24 dwarf companion galaxies of our Milky Way, whereas half of them were counted until then. One of these galaxies, named Seg-1, is 75,000 light-years distant from the Milky Way. 1 billion times fainter than our galaxy, it appears to be composed mainly of dark matter, with only a few hundred stars scattered in its bowels. Seg-1, despite an extremely low luminosity, which does not exceed that of 300 suns, because of its practically insignificant number of stars, is considered as a dwarf spheroidal galaxy. Its mass corresponds to about 600,000 suns, which is too large for a globular cluster, especially since its stars are rather similar to those usually found in galaxies. This lack of luminosity, associated with a very compact structure and a low concentration of metal, seems to indicate that this is a very old celestial object, which will probably have encountered, during its cosmic wanderings, the gravitational disk of our galaxy. But what remains a mystery is the mass of this object, which cannot be explained by the presence of a black hole. Indeed, the stars present do not swirl ardently around an object that would be massive. Consequently, Seg-1 does not have a massive black hole in its center, which could explain this important mass. No other matter in sufficient quantity like hydrogen gas in astronomical accumulation or dust can explain this mass. Seg-1, would thus be the only dark matter galaxy in the universe. A little further away, another galaxy was discovered during the same study program, Sloan Digital Sky Survey in the Aries galaxy, the Seg 2 Located at about 114,000 light-years from the Sun, this small galaxy is approaching our Sun at a speed of 40 kilometers per second, or 25 miles per second. Its stellar population is composed mainly of old stars, formed more than 12 billion years ago. No newly formed stars are present. Their metallicity is very low. They would contain at least 100 times less heavy elements than our Sun. You are probably looking at the oldest stars in the universe. Seg 2 contains only 1,000 stars and some dark matter that binds them together. Its luminous power is strongly impacted. It is barely 900 times brighter than the Sun, which is ridiculously low compared to the Milky Way, which shines 20 billion times brighter. The Seg 2 galaxy is thus one of the faintest galaxies known to date, weighing at least 10 times less than previous estimates for such objects. This is a new challenge to the theoretical understanding of structure formation in the universe. Let's now visit the Great Dog Dwarf galaxy, which is our closest neighbor and is located on the periphery of our solar system. It is about 25,000 light-years from the Sun and 42,000 light-years from the center of the Milky Way. It is located, as its name suggests, in the constellation of the Great Dog. It is a small, irregular galaxy whose mass is equivalent to nearly 1 billion solar masses. Long hidden behind the plane of the Milky Way, hidden by the dust and gas trapped in its disk, it was discovered only recently. It is thanks to an infrared survey, allowing astronomers to see many regions of space well beyond the disk of our galaxy, that it was detected for the first time in 2003, dethroning then the dwarf galaxy of Sagittarius of its status of closest galaxy. Rather elliptical in shape but irregular, it is home to 1 billion stars, including a large number of red giants, which in fact represents only a small percentage compared to the Milky Way. Its main body, of jagged and fragmented appearance, is thus of irregular shape. This degradation seems to be the consequence of the accretion to the Milky Way that it inexorably undergoes. Undergoing the tidal forces of the latter, it is literally torn apart, leaving in its wake a long filament of stars. It is so long that it goes 3 times around the Milky Way, taking the form of a ring known as the unicorn ring. It looks like there are other remnants that have not yet been completely swallowed up. There are several globular clusters which have been discovered in different constellations: the Dove, the Hare, the Stern, and the Carina, and which would have been separated from their host. I propose you now to join the constellation of the Great Bear, this immense constellation, which decorates our starry sky with a famous Big Pan. Adorned with countless stars, it is home to a magnificent planetary nebula. But above all, there are no less than 50 galaxies, including the Big Dipper 1 galaxy, also called Ursa Major 1. This galaxy, with low surface brightness, is 316,000 light-years away from our Sun. It is one of the 3 least luminous galaxies recorded to date. In comparison, it is less luminous than the star Deneb, which is in our Milky Way. It is made up only of population 2 stars, that is to say, old stars with low metallicity. You can find similarities with the dwarf galaxy Sextant 1. It is, like its cousin, old and poor in metals, and measures only a few thousand light-years in diameter. Let's take the opportunity to visit the Great Bear II dwarf galaxy, also known as Ursa Major II or UMA II. Discovered at the same time as the previous galaxy, it is about 30 kpc from the Sun, or about 97,800 light-years. Its luminosity is about 4,000 times that of the Sun, which is well below the vast majority of globular clusters that we can admire. It is even less luminous than some stars in our galaxy, such as Canopy, for example. The majority of the stars in this galaxy are population 2 stars, that is, stars of advanced age. The formation of these stars probably dates back to more than 10 billion years. Their relatively low metallicity index is estimated at more or less 0.06, which means that they contain 300 times less metal than our Sun. However, its total mass is equivalent to nearly 5 million solar masses, if we count baryonic matter and dark matter. Its mass to luminosity ratio is then of the order of 2,000, which seems to be strongly overestimated, especially since its irregular shape shows that it is strongly perturbed by the galactic tidal forces induced by the Milky Way. Unfortunately, this satellite, which is one of the smallest and weakest orbiting our galaxy, is approaching our Sun at a speed of 116 kilometers per second, or 70 miles per second. The Big Dipper 2 is inexorably subject to tides that cause strong disturbances over time, even irreversible dismantling. We could continue our journey through many such galaxies, including the Willman 1 galaxy, also located in the constellation of the Big Dipper, the Bouvier dwarf galaxy, the Berenice Hare dwarf galaxy, the Hercules dwarf galaxy, the Pisces II dwarf galaxy, or the Aquarius II dwarf galaxy. If all these galaxies have many points in common, I propose, however, that we linger with the Reticulum II galaxy, which is located in the southern constellation of Reticulum, halfway to the Magellanic Clouds. Its recent discovery dates back to 2015 and was only possible through the exploitation of data collected by the DES, Dark Energy Survey, which is an international optical and near-infrared survey research program. But Reticulum 2 did not reveal itself alone. It was spotted along with 8 other dwarf satellite galaxies orbiting the Milky Way. This discovery surprised astronomers who did not expect to find so many satellites in such a small area of the sky. Reticulum 2, which is probably spheroidal, is only 104,000 light-years away from our solar system, making it one of the closest Milky Way satellite galaxies. This object, called ultra-pale, like all the ultra-faint spheroidal dwarf galaxies we have just visited, contains very little observable matter. This small structure probably contains no more than 5,000 stars, themselves representing little more than 1% of the observable matter. Composed essentially of dark matter, which itself is only detectable by its gravitational attraction, this galaxy is 1 billion times darker than our galaxy and 1 million times less massive. If you observe it closely, you can see how it is being torn apart by the massive tidal forces it is undergoing as it comes into contact with the Milky Way. The discovery of these dwarf satellites in a handkerchief of pocket proves to be disconcerting and questions once again the scientists. Are they ancient satellites that orbited the Magellanic Clouds and were ejected by the interaction between the small and large Magellanic Clouds? Or were they originally part of a gigantic group of galaxies, destined, like the Magellanic Clouds, to be devoured by our own galaxy? What about you? What do you think? The vast majority of spheroidal dwarf galaxies occupy a position in space quite close to the two main members of the local group, namely the Milky Way and the Andromeda galaxy, to which they are gravitationally bound. Most of them are gathered in a perimeter of only 7 million light-years. However, some dwarf spheroidal galaxies prefer to play solitary. These galaxies, which seem to have stepped out of line, are called isolated galaxies. What might an isolated galaxy look like? How does it behave in the universe? But above all, how did it form? This is what we will try to elucidate by getting closer to some of them. Let's start by visiting the Dwarf Whale Galaxy, which was long camouflaged in the constellation of the same name until its discovery in 1999 by a member of Cambridge University. It is respectively 2.46 million light-years away from the center of the Milky Way and 2.2 million light-years away from the center of the Andromeda Galaxy. Like its congeners, it has a low surface brightness. Its stellar mass is estimated at 2.6 million solar masses, while it appears to be devoid of hydrogen, so much so that this gas is not detectable. Its population of stars is relatively old. They would have been formed 12 billion years ago, during a short period of 2 to 3 billion years. It is therefore 8 billion years since no new stars appeared in the heart of this galaxy, which looks so peaceful. The effective radius of this galaxy is barely 2,300 light-years. Its radial velocity of 87 kilometers per second, or 55 miles per second, brings it slowly closer to our Sun, while its dispersion velocity is about 17 kilometers per second, or 10 miles per second. If you take a few moments to contemplate it, you will notice that it has a global rotation speed of about 8 kilometers per second, or 5 miles per second. This group of old, cold stars, like a ghost ship carried by weak cosmic currents, seems to wander in the universe like a lost soul. Another cluster of small stars, very faint and devoid of gas, was discovered in 1990 at the Mount Stromlo Observatory in Australia. This is the Toucan Dwarf Galaxy. Like the Whale Dwarf Galaxy, its surface brightness is relatively low, and its population of stars is comparable, most of them 13 billion years old. This tiny spheroidal galaxy is even smaller than the Whale, its effective radius being just over 926 light-years. It is about 2.8 million light-years away from our galaxy, and nearly 4.4 million light-years away from the Andromeda Galaxy. But what makes it even more special is its position in the local group. If, like isolated galaxies of the same kind, it is at a certain distance from the two referent galactic monsters, on the other hand, it is located almost opposite most of the other members in relation to the Milky Way. Unlike many galaxies, it has a positive radial velocity, meaning that it is moving away from our Sun at a speed of 194 kilometers per second, or 120 miles per second, with a low velocity rotary motion, estimated at 16 kilometers per second, or 10 miles per second, in its outer regions. Among the isolated spheroidal dwarf galaxies, we can also mention KKR 25, located in the Dragon Galaxy. The latter was discovered in 1999 by 3 researchers who gave it their name, namely Karachentsev, and Richter. Like the 2 previous galaxies, it is characterized by its distance from the main members of the local group, estimated at more than 6 million light-years, but especially by its isolation from any other cosmic object. Another isolated galaxy attracts the scientific community, the KKS3 galaxy. Difficult to spot because of its low luminosity, it is barely 7 million light-years away from the Milky Way. Its discretion is all the more important, as its total mass is about 20 million times that of the Sun. If it was detected in 2000, its isolation could be proven only in 2014 thanks to the Hubble telescope. The majority of the stars that compose it are old stars, formed probably 12 to 14 billion years ago. Devoid of gas since then, it has not created stars for a long time. It is therefore a relic that greatly interests astronomers because of its great age, but above all, because of its isolation. It has probably not undergone any change for a very long time, which makes it an ideal research laboratory to understand the cosmic workings and the foundations of the universe. The Hubble Space Telescope has been steadily revealing its findings since its launch in 1990. In 2018, it detected a galaxy that until then had gone unnoticed, as if forgotten, and for good reason. While scientists were observing the globular cluster NGC 6752, 13,000 light-years away from our solar system, in search of its faintest stars, a never-before-detected dwarf galaxy quietly appeared in the background, in the constellation Peacock, in the form of a very dense and elongated collection of faint stars. Distant by about 30 million light-years, the Bedin 1 galaxy was thus also the object of an accidental discovery. Hidden behind the bright stars of the cluster studied, this spheroidal dwarf, which places it in the category of isolated galaxies. It is even to date the most isolated galaxy of this type. Its closest neighbor is 2.12 million light-years away. NGC 6744, a large intermediate spiral galaxy, also located in the constellation Peacock. For the time being, it is not yet known whether these 2 galaxies are gravitationally bound, nor whether NGC 6744 is its host. But what makes Bedin 1 even more spectacular, apart from its isolation, is its age. Examination of its light spectrum, which is about 1,000 times smaller than that of the Milky Way, has led scientists to conclude that it has a very low concentration of metals. This galaxy, which was probably born during an explosion, has not experienced any new period of star formation since then. The stars in it are therefore very, very old. Bedin 1 seems to be one of the oldest galaxies ever discovered, and would be 13 billion years old. If you add 0.8 billion years to it, Bedin 1 would be as old as the universe. Considered by astronomers as a kind of living fossil of the primordial universe, having undergone no interaction with other cosmic monuments, it looks like a time capsule. Its preservation of the conditions of the primitive universe should still be able to give us many secrets concerning its creation. New generation telescopes, such as the W-FIRST telescope, should in the near future bring to light many other galaxies of this type, which have remained discrete for a long time because of their very low luminosity. As you can see, these objects have not finished to be talked about. I propose to you now to be interested in another category of galaxies. Let's discover some of the most beautiful irregular dwarf galaxies that embellish the local group with their colorful twinkling. Let's first discover the IC10 galaxy, located in the northern constellation of Cassiopeia, about 2.2 million light-years from our Sun. You immediately notice that it is much brighter than all the previous galaxies. Of course, it does not dazzle by its size, its diameter being about 5,000 light-years. No, it is by its different regions reflecting a reddish glow through intermediate dust clouds that it stands out. Unlike its fellow galaxies, the IC10 galaxy has a large population of newly formed massive stars. You are in front of the only starburst galaxy, i.e., a star-forming galaxy belonging to the local group. It contains more Wolf-Rayet stars, hot stars of several tens of solar masses, then the Magellanic Clouds, although much smaller. Observe its central part, where a large X-ray source can be detected. A high-mass X-ray binary is located there. It is composed of a Wolf-Rayet star and a compact object, which is none other than a stellar black hole, whose mass reaches several tens of solar masses. Look how these star formations punctuate the heart of this galaxy. Their production represents between 0.04 and 0.08 solar masses per year. The interstellar gas that feeds these numerous outbreaks can probably last for several billion years. What a magnificent sight! Now, look at the hydrogen envelope that surrounds this galaxy with its vaporous mantle. Look carefully. Its movement is different from that of the galaxy itself. Surprising, isn't it? Another isolated galaxy intrigues the astronomer's sphere. This is the Leo 3 galaxy, also named Leo A. As you have understood, it is located in the constellation of Leo. Distant from 2.25 million light-years from our Sun, it is also an irregular dwarf galaxy, whose mass probably does not exceed 800 solar masses. This gas-rich galaxy has a low stellar mass and low metallicity. Its largest diameter is about 6,500 light-years. It contains stars of different ages. The youngest are approximately 10 million years old, while the oldest are up to 10 billion years old. However, over 90% of its stars were formed less than 8 billion years ago. In total, it hosts 5 star clusters, 2 young low-mass clusters and 3 older ones, also low-mass. Despite these many stars, this galaxy is still 80% dark matter, which is still a mystery. You can admire its ancient halo of stars, which was discovered a few years later, in 2004. Take a closer look at this galaxy. Its internal ring structures remind you of the typical morphology of spiral galaxies. Its stars extend beyond its gaseous envelope. It thus resembles massive disk galaxies and proves that galaxies of very low stellar mass are just as capable of creating complex structures. Here is, once again, a galactic object that challenges the current understanding of galaxy evolution. Our journey is coming to an end. However, I would like to allow you to discover two last galaxies, which of course do not belong to the local group, but which are so close to it that we cannot be satisfied with observing them from far. It would be a shame to give up visiting them when we have never been so close to them, wouldn't it? Among the galaxies that populate the near periphery of the local group, I propose you to discover one of them, long considered wrongly as an irregular galaxy. Let's go to the constellation of the Sculptor, where we can admire the galaxy NGC 55, also named Cadwell 72. In the distance, it hides behind its flattened shape, making it look like a long, graceful comet with its disparate tails. In fact, it only lets us admire its narrow profile, extending over about 68,000 light-years. But look closely. As we get closer to it, we can change our angle of view. Isn't that wonderful? Look at this galactic object that is slowly being revealed. Doesn't it look strangely like the large Magellanic Cloud? You can now contemplate this galaxy, which offers us a complete vision of its structure. In reality, Cadwell 72 is a barred spiral galaxy. Composed of a single arm, it falls more precisely in the category of Magellanic spiral galaxies. However, unlike the Magellanic Clouds, which are about 180,000 light-years away, this small galaxy is almost 7 million light-years away from our solar system. It is probably the closest galaxy to the local group known to date. Several 100 billion stars illuminate its flattened disk, but you can see how much denser and brighter its center appears. This is its bulge, characterized by this central and spherical bulge. This core, particularly bright, is crossed by clouds of dust. In some places you can observe iridescent colored areas. There are many regions of pink star formation, but also young clusters of blue stars, which testify to the activity that still reigns within this small galactic monster. Not far from there, another luminous object attracts our attention. Still in the constellation of the Sculptor, another spiral galaxy is next to the object, NGC 55. It is the galaxy NGC 300, or Caldwell 70. This one is also about 7 million light-years away from our Sun, is a low-surface brightness galaxy, its light being spread over a larger apparent area. If you look closely at its structure, you will see that it is not unlike our Milky Way. Its luminous halo, which extends over more than 55,000 light-years, is dotted with swarms of red giant stars that straddle its two spiral arms. Its bulb, too, has myriads of stars. Moreover, this galaxy has been the subject of many studies. It has even been portrayed. This feat is the result of 50 hours of exposure, spread over a number of nights of observation. The Wide Field Imager camera, which has a very large field of view comparable to that of the apparent surface of a full moon, was able to take a large number of pictures, which once processed with special filters and assembled, allowed the creation of a unique image. In addition to mapping this galaxy, which is comparable to our own in structure, it has revealed that it harbors a black hole of about 15 solar masses at its heart. This black hole belongs to a binary system and is close to a hot and luminous Wolf-Rayet star. Finally, only 1 million light-years seems to separate these two cosmic objects, namely NGC 55 and NGC 300. This galactic pair is most likely gravitationally bound. Do you think that one of these galaxies is destined to devour its sister? Or will they both be absorbed by an even more powerful galactic monster? Dear traveler, good morning. Today we will discover these gravity wells, often compared to cosmic monsters. We will meet black holes, from the largest to the most unusual. But before leaving for a new adventure, think of liking the video and subscribing to the channel to not miss anything. Thank you, and have a nice trip! We are now going to start our interstellar journey. I advise you to fasten your seatbelt. Well, because we are going to cover unimaginable distances in a ridiculous time. But before we leave our solar system, let's tear ourselves away from our beautiful planet Earth and head for Mars. Half the size of Earth, it is easy to recognize by its red color. As we fly over it, you can see the ice caps that cover its two poles. Observe its rocky and deserted surface, dotted with deep gorges, but also with numerous volcanoes, some of which are truly impressive in size. If it evolves in the habitable zone of the Sun, unfortunately, its mass and its relatively weak size will probably never have allowed life to develop there, at least not for long. Let's not linger too long in the environment of Mars, because 2 moons orbit around it at only 9,400 and 23,500 kilometers of the distance, or 5,800 or 14,600 miles. Small in size, measuring respectively 27 kilometers or 17 miles and 15 kilometers or 9 miles, they could surprise us, especially since they are both black as coal. Our trajectory inevitably leads us in the direction of the asteroid belt that separates Mars from Jupiter. We have to cross this unusual boundary, which is littered with obstacles, marking the border between the inner and outer solar system. Hundreds of thousands of objects orbit in this zone. If most of them are small, even insignificant in the form of dust, nearly 800,000 of them measure a few tens of meters or feet to several hundred kilometers or miles. The largest belong to the class of planetoids. You can recognize Vesta, which is roughly spherical, with flattened poles and an equator that seems to have large gashes in it, comparable to those in the Grand Canyon. The surface of the asteroid also bears the multicolored scars of numerous impacts. Depending on their violence, but also on the nature of the object involved, the stigmata display different colors due to various chemical compositions. Let's now observe Pallas, an asteroid whose orbit is inclined. It is relatively spherical in shape, and its surface is riddled with small craters, giving it the appearance of a golf ball. It is also the object of the belt which presents the most impacts on its surface. Unlike all other asteroids, Pallas has a unique orbit. It must therefore make its way through the many other objects that evolve in the same flow. This asteroid consequently undergoes collisions more important than its companions, both in frequency and intensity. Vesta and Pallas, which have a diameter of a little more than 500 kilometers, or 310 miles, are to date the two largest known asteroids of the main belt. However, they have only occupied the first place for a few years because Ceres, with its 950 kilometers, or 590 miles, was until then the star. Ceres still orbits in the heart of the main belt. It has not disappeared. But since 2006, it has been integrated by the International Astronomical Union to the family of dwarf planets because of its spherical shape. In spite of the asteroid belt, our journey is going smoothly because we can take advantage of the Kirkwood gaps, those areas almost devoid of objects, to make our crossing as serenely as possible. Let's leave this rocky region. Our progression now leads us to the approaches of the imposing gaseous planet Jupiter, the largest and heaviest celestial body of our solar system, after the Sun. Its important mass and gravity confer it the quality of guardian of the system. Indeed, these characteristics allow it to attract comets and asteroids to it. It acts as a shield, preventing these objects from crashing into the inner planets, such as the Earth. But let's not change our trajectory and continue our progress. We are approaching Saturn. You have, of course, identified it from afar, thanks to its rings. But look closer. Have you ever noticed this geometric shape on the North Pole? Like a gemstone embedded in the center of a jewel, a gigantic hexagonal storm, measuring more than 32,000 kilometers, or 20,000 miles in diameter, crowns this planet. Formed by the clouds of the troposphere, this shape, which seems to be drawn with a chalk line, is the consequence of jet streams which blow at more than 320 kilometers per hour, that is to say 200 miles per hour, thus drawing each of its 6 faces. Let's leave this fantastic cyclone far behind us and go to the limits of the solar system, in the direction of 2 ice giants. We first cross Uranus, which is easily recognizable by its atypical behavior. Its inclination of about 90 degrees with respect to the plane of its orbit gives the impression that it rolls like a ball around the Sun. Our journey continues with a flight over the 8th and last planet of the solar system, Neptune. This planet, with its azure blue hues, is far from the tranquility of a clear sky. It is whipped by supersonic winds that can exceed 2,000 kilometers per hour, or 1,242 miles per hour. Let's not linger near this giant that suffers from the apocalyptic climate and dive into the immense Kuiper Belt, located between 30 and 55 astronomical units from our Sun. This immense zone extends over several hundred million kilometers or miles and contains hundreds of thousands of celestial objects. Several dwarf planets also orbit in the heart of this structure, which is one of the largest in our solar system. If some of these objects may have been recently caught by the belt's gravitation, the majority of them are pieces of rock and ice. They are probably residues of the formation of planets, which would have been ejected in this distant region because of the interactions undergone by the 4 giants that we have just crossed. As you have seen, no black hole has crossed our path, at least not formally, and for good reason. To date, no such structure has been detected in this region of space. But exactly, what is a black hole? A black hole is a region of space where the gravitational pull is so strong that no matter or radiation can escape, not even light. even though it is the fastest thing in the universe. This strong gravity is induced when matter has been compressed into a tiny space. Considered nevertheless as a celestial object, a black hole can neither emit nor diffuse light. A black hole is therefore invisible. Knowing that they absorb all the light in their invisible center, you may wonder how the existence of black holes could be confirmed. If they are invisible directly, the use of indirect observation techniques in different wavelengths allows to detect their presence. Indeed, if we are not yet able to describe the central region of a black hole because of its gravitational singularity, we can study the physical conditions of its immediate vicinity and its influence on its environment. This is why only 3 parameters can be described. These are the mass, the electric charge, and the angular momentum. As black holes are not visible, these parameters allow astronomers to detect their presence by the effect they produce on objects that come too close. For example, a star can see its trajectory influenced by the presence of a black hole around which it orbits. Similarly, when a star and a black hole are in close orbits, scientific instruments can identify a high-energy light that is then produced. If the gravity of the black hole is strong enough, it can extract the outer gas from the star in question and form an accretion disk. This disk spirals around the black hole, releasing X-rays in all directions. Another phenomenon can be seen when matter falls into such a cosmic hole. This matter will overheat, just like the gas of a nearby star, and emit strong X-rays, which can consequently also be detected by scientists. A question is certainly on your mind. If black holes are invisible, can we still describe them? The answer is yes. On the one hand, scientists have been able to study them, thanks to the previously described techniques. But moreover, an image has been shown around the world in 2019. The international team of the Event Horizon Telescope was unveiled after 2 years of data processing and more than 10 years of work, the first ever photo of a black hole. It is the picture, made with very long baseline interferometry, of the supermassive black hole M87, nestled in the heart of the galaxy M87, located 55 million light-years from Earth. We can discover a black disk surrounded by a ring of light, corresponding to the shadow of this colossal object. Its mass is equivalent to 6.5 billion solar masses, and the diameter of its event horizon is estimated at 254 astronomical units. That is, 254 times the distance to the Earth and the Sun. But let's take a closer look at this strange object in order to reveal its structure. A black hole is composed of an external event horizon, a second internal event horizon, and its singularity. The event horizon marks the limit around the mouth of the black hole. As soon as a particle enters this horizon line, it is trapped and doomed to disappear. Gravity is constant in this zone, whatever the distance. However, it happens that matter, attracted by the black hole, ricochets on the event horizon. It is then projected outwards, accompanied by a shower of light jets of matter. The singularity represents the inner region of the black hole. This is where the overwhelming mass of the object remains. The singularity is completely hidden and corresponds to the unique point where the mass of the black hole is concentrated in space-time. But how can such a cosmic phenomenon occur? Scientists believe that some black holes, called primordial, appeared shortly after the Big Bang in the early universe. Supermassive black holes have been discovered in some galaxies, which also suggest that they were created at the same time as their host galaxy. Another category of black holes could be the result of the death of a massive star when it collapses on itself, causing a supernova. If a black hole occupies zero space, it has a very large mass. This mass represents the major part of the mass that was once that of a star. Of course, as gluttons, black holes become more and more massive as they gobble up the surrounding matter. The zone of no return, i.e. the event horizon, gradually grows with the black hole. The existence of black holes in the universe can lead to another reflection. If they absorb everything in their path, can they represent a real danger? But first of all, are there many of them, or are they quite rare anomalies? Since black holes are difficult to detect, since they are as black as the space in which they are located, only theoretical calculations can establish an estimate of their number. According to some researchers, there could be millions of small black holes not yet detected in our interstellar neighborhood. They rely on modeling the evolution of galaxies over the billions of years that have already passed. Based on the numerous observations and statistics established on the evolution of galaxies, they were able to determine demographic trends. Some galaxies are true nurseries of stars, while others seem to have exhausted their reserves and no longer produce anything of note. By also taking into account the metallacity of a galaxy, i.e., the metal content inside it, they can similarly determine whether it is a good candidate for star production. Thanks to these building blocks, a model of the stellar population within galaxies allowed them to quantify the number of stars appearing in the universe by categories: small, medium, and large stars. Their evolution could then be estimated. The evolution of black holes has also been included in the scientists' calculations. Some can swallow a double system, taking advantages of these ingestions. Others, at the end of their life, continue to attract the surrounding gas. A merger between two black holes is another possibility. All these parameters have allowed scientists to make an astronomical census of black holes. They found that in each cubic megaparsec of the universe, or 3.26 million cubic light years, there could be as many as 50 million solar masses of black holes. Insofar as a single black hole would have the mass of our Sun, this would correspond to about 50 million distinct black holes in this same space. In other words, black holes could be frighteningly common in the universe. Are you ready to get close to one of these black holes? Do you know which black hole is closest to Earth? Unicorn. This is the name given to the tiny black hole closest to Earth that resides in the constellation Monoceros, more commonly known as the Unicorn. It has been spotted only recently, in 2021, only 1,500 light-years away. On the scale of the cosmos, it is located 2 steps from our beautiful planet. But traveling at the speed of light, it would take us no less than 1,500 years to reach it. It has a mass equivalent to 3 times that of our Sun. In comparison, the black hole at the heart of our Milky Way contains 4.3 million solar masses. Its discovery, which cannot be due to its size, ridiculously small for a black hole, was made by the observation of a red giant star that evolves alongside it. The latter, which is approaching the end of its life, is subject to an invisible gravitational force that causes a slight distortion of its light, as well as very slight variations in its speed. Detecting such a structure is almost impossible, because the smaller the black hole, the weaker its impact on neighboring structures. What makes this black hole particularly intriguing is that it appears extremely light for such a cosmic object. Indeed, for scientists, black holes could not have a mass less than 5 solar masses, which calls into question their theory, while opening new and fascinating perspectives to finally hope to understand the mechanisms that govern the formation of neutron stars and black holes. On the other hand, black hole hunters focus their attention on binary systems. Although these objects are extremely discrete, they could well be much more numerous than one would think. They are convinced that this small black hole called Unicorn could be the first of many, and estimate that between 100 and 1,000 could be detected in our own galaxy alone. Among these numerous objects, some are more visible than others, and therefore more easily detectable. However, a dark and isolated black hole was discovered fortuitously by scientists using the gravitational microlensing technique while observing a much more distant star. The peculiarity of this object, detected in 2011, is that it seems to drift alone in interstellar space, like a castaway in space, far from any host galaxy, but especially without a larder nearby. Like an orphan, it is distant from our solar system by about 5,153 light-years in the direction of the galactic bulge in the constellation Sagittarius. This black hole, named OB 110462, has been studied with the Hubble telescope. Its mass is estimated at 7.1 times that of the Sun, and its speed at nearly 45 kilometers per second. That is to say, more than 28 miles per second. For the scientific community, this isolated stellar black hole, whose age is estimated at 100 million years, could be the first of a long list. The death of large stars leaves room for black holes. There must be hundreds of millions of them scattered in our galaxy. Their observation finally possible by the gravitational microlensing technique opens new opportunities to finally detect these dark and compact objects that probably populate the Milky Way. And who knows, maybe one day soon, one of these invisible black holes will turn out to be a primordial black hole, giving us secrets about the period of the famous Big Bang. Let's continue our journey and head for the constellation of Cygnus, which has a stellar black hole, the first to have been discovered using X-ray detectors. Distant from our solar system by 7,237 light-years, it was the first candidate as a black hole. It is part of a high-mass binary system that was identified in 1965. Its companion, a blue supergiant, is a variable star with a mass of about 25 solar masses. This star, probably 5 million years old, is oscillating under the gravitational attraction of the black hole Cygnus X1, which has a mass of about 20 times that of the Sun, for only 120 kilometers or 75 miles in diameter. These two objects orbit each other very quickly. Indeed, their period of revolution lasts only 5.5 days. Cygnus X1 rotates faster than any other object of the same nature examined to date. its speed is close to that of light. Thus, this stellar black hole evolves at a frantic speed next to a companion which is slowly disintegrating at its side under the effect of its gravitational attraction, offering it, in spite of itself, its cosmic dust as a meal. This devoured matter provokes important jets of matter, classifying this black hole in the category of quasars. But how did it form? The absence of a residual nebula in the black hole's surroundings, which has been studied for a long time, allows scientists to consider that it appeared as a result of a simple gravitational collapse of a supernova star, but without explosion. You probably think that black holes are all alike, but you are wrong. While it's true that they generally have common characteristics, one black hole alone defies scientists' understanding of how they form. Let's go and discover MaxiJ 1820 plus 070, an atypical black hole of our Milky Way, located at about 10,000 light-years from the Earth, in the constellation of the Serpentare, Ophiuchus. This stellar black hole has a mass of about 8 times the mass of the Sun. It is slowly but surely stripping away its close companion, a white dwarf, whose mass is equivalent to half a Sun. As with other black holes, the matter that is not engulfed is expelled into the cosmos in the form of jets. However, when you see it in your line of sight, you immediately notice that it is not like its cousins. This cosmic object is distinguished from other black holes by a misalignment between its axes of rotation. Indeed, a binary system of this type, with a star orbiting a black hole, should present, in the absence of extrinsic perturbations, axes of rotation aligned with each other, and especially perpendicular to the orbital plane. However, as you can see by looking closely at this structure, it is not so. The inclination of the black hole and its orbit have completely different axes. The axis of rotation of the black hole is tilted by more than 40 degrees with respect to the axis of the orbital plane of this binary system, making it unique in its kind. The trajectory of the double jet of hot matter thus appears strongly misaligned with respect to the axis of rotation of its orbit. For the researchers, this strong misalignment was probably shaped at the formation of the black hole, even before the system had time to straighten up. A supernova, the giant explosion of a star at the end of its life, which was at the origin of this black hole, will probably have caused this asymmetry under the impact of its incredible violence. MaxiJ 1820 plus 070 is also known to the scientific community for having captured one of its countless explosions on video in 2018 at NASA's Chandra X-ray Observatory. The video allows for a time-lapse or video animation of one of its eruptions, but also allows for the study of the velocity of hot material expelled into space by the black hole within its pair of opposing jets. The first findings noted speeds of the order of 60% of the speed of light for the North Pole and 160% of the speed of light for the South Pole. But what is really the case? In fact, the real speed of the rejected particles is about 80% of the speed of light, which represents a speed close to 863 million kilometers per hour, or more than 536 million miles per hour. The first findings were truncated by the illusion of transluminal velocities that occurs when the jets of the black hole are almost parallel to the direction of the observers based on our planet Earth. This black hole is a perfect example of this, as its jet emitted at the South Pole is approaching the Earth, while the one at the North Pole is moving away from it. Do you see these two powerful and condensed jets? To give you an idea of the amount of matter being ejected, astrophysicists have estimated that it is about 500 million times the mass of the Empire State Building in just a few hours. This fantastic amount of matter produces real shock waves before slowing down as it enters the interstellar medium. But let's not get too close to this structure. If we know the risks of crossing the accretion disk of a black hole, we cannot yet predict the eruptions followed by the emission of jets of matter. Even a small black hole remains an endless sink that never gives back what it has made disappear. Let's see now, what are the particularities of low-mass black holes? In other words, stellar black holes. I propose that we go to a binary system in our Milky Way, known as XTE J1650-500, which could have housed the smallest black hole ever detected. To do this, we must reach Ara, a constellation in the southern hemisphere that borders Scorpio. Located more than 10,000 light-years away, this binary system was spotted in 2001 by NASA's Rossi X-ray Timing Explorer satellite and seems to have a stellar black hole at its heart, whose mass is particularly light for this type of object. Initially estimated at 3.8 times the mass of our Sun, the mass of this structure, which measures only 24 kilometers or 15 miles in diameter, has finally been revised upwards. It would actually be between 5 and 10 solar masses. But stay on your guard. This structure, as small as it is compared to its companions, could attract you, and under its gravitational force, you could still end up in astro spaghetti. Another candidate black hole is potentially the lightest of all. It is IGR J17091, a stellar mass black hole located in the constellation of Scorpio, 28,000 light-years from our solar system. Discovered by the Integral satellite of the European Space Agency, it would have a mass between 3 and 10 times that of the Sun, making it a small cosmic monster, and that is an understatement. Winds of formidable intensity have been observed in the disk surrounding this black hole, reaching nearly 3% of the speed of light. Its winds are as violent as those that can be measured in structures such as supermassive black holes, which are up to billions of times heavier. Moreover, the winds of IGR J17091, which originate from the gas disks surrounding the black hole, have revealed to have a very unexpected feature. It seems that they are able to carry away much more cosmic material than the black hole captures. So you can imagine that these winds take in gas from the adjacent star before the black hole blows it away forever, then expels it into the cosmos. In reality, it turns out that the champion of the lightweights is the unicorn black hole, which also has the distinction of being the closest black hole to our Earth to date, as we found at the beginning of our expedition. I propose to continue our journey in the heart of our galaxy. Let's go and discover the star Sagittarius A. As its name indicates, the black hole Sagittarius A is located in the constellation of Sagittarius, 26,673 light-years from the solar system, more precisely, in the heart of the Milky Way. This area of space, named Sagittarius A, has been suspected of hosting a black hole since the 1930s, but it was in 1974, at the Green Bank Observatory in West Virginia, with the help of one of the largest steerable radio telescopes in the world, that it was actually identified. If at that time this compact radio source was revealed, it was in the 1980s that astronomers began to hypothesize that the central compact object was probably a black hole, whose size seemed implausible. After studying the stars near this intriguing source of radio waves for a decade, they found that they seemed to swirl around a dark object, evolving in the heart of the Milky Way. From their movements, they then assumed that a black hole of 4 million times the mass of the Sun was interfering with them. Subsequently, other assumptions were discarded, including the presence of mini-stars very closely grouped. It was in 2017 that evidence of a supermassive black hole was provided through the Event Horizon Telescope, a multinational research project which produced a resolved image of the accretion disk all around. This image, which is the second in astronomical history for this type of object, confirms that Sagittarius A is a black hole with a mass of more than 4 million solar masses. This finding corresponds exactly to the predictions of Einstein's theory of general relativity, and provides valuable clues about the functioning of black holes and de facto galaxies. You can imagine how difficult it was to expose this dark object, drowned in a bright orange halo, so much it is masked by the gases that surround it. These extend between 5 and 30 light-years, and occasionally offer it a little energy to devour, causing faint X-ray flashes. Temperatures in the accretion disk can reach up to 10 million degrees Celsius, or more than 18 million degrees Fahrenheit. Take a moment to contemplate Sagittarius A and realize that the entire Milky Way, more than 13.6 billion years old, orbits around it. Relatively discrete and not very active, this supermassive black hole that shaped our galaxy still holds many secrets. It is true that black holes are considered to be silent cosmic monsters, only impacting the too curious matter that travels alongside them. However, one of them turns out to be threatening far beyond its event horizon. If you want to know more, we must approach another binary system, composed of a regular lambda star and a black hole, located near the constellation of Scorpio, about 28,000 light-years from our solar system. Let's get to this intriguing object, named H1743-322, without further ado. I won't keep you waiting any longer, and will now reveal what makes this black hole so different from its peers. It turns out that it shoots bullets. 2 balls of high-energy material were ejected into space by this little black hole in 2009, as if it were expelling bulky burps from its poles during a difficult digestion. Moreover, studies conducted so far have shown that it seems to feast without restraint every 8 months, swallowing a large amount of matter that is drawn into its accretion disk that reaches millions of kilometers in diameter. This periodicity is evidenced by the measurement of cyclic variations of X-rays called quasi-periodic oscillations. A black hole firing ultra-fast gas bullets into the cosmos, reaching a quarter of the speed of light, or about 270 million kilometers per hour, or 170 million miles per hour, is a most surprising phenomenon. But what makes it even more curious is that these radio spots, which accompany the usual particle jets, occur at a time when radio explosions are not yet observed. How do scientists explain this phenomenon? For the moment, none of them has an answer, and theories are intermingled. But what is certain is that the accretion disk and the launch of jets are related to this cosmic strangeness. But let's not stay too long in this somewhat uncertain environment, and prefer a less explosive destination. I now propose that we resume our journey. Let's teleport to another area of the universe, in the constellation of the Big Dipper, close to the Bode nebulas, two galaxies so close that they were discovered at the same time. Let's take a look at one of these two neighboring galaxies, the one that harbors the rarest type of black hole known to date, the Cigar Galaxy, or Messier 82, distant from our Sun by only 12 million light-years. This galaxy has two symmetrical bluish spiral arms that stretch around its core, where at least 197 young massive star clusters are evolving. Each of these clusters has a mass close to 200,000 solar masses and cohabits around a center that produces stars at a rate 10 times faster than that of the entire Milky Way. As a proof, this magnificent galaxy called Starburst, whose disk is 5 times more luminous than that of the Milky Way, has a center which is hundreds of times more luminous than that of our galaxy. The diameter of its central region, which is very active in star formation, is about 500 parsecs, or more than 1,630 light-years. There are 4 beautiful star clusters in this region, where significant X-rays are detected. Look closely. We may be witnessing a supernova, which seems to be legion in this busy area. As expected, a supermassive black hole is located in the center of this galaxy. The mass of the latter is estimated at 30 million solar masses. Of the object, there is no longer any doubt. It is indeed a second black hole, named M82X1, in reference to its host. Its mass is estimated to be between 400 and 500 times that of our Sun. It seems that a giant star, or even this discovery is significant because it confirms, after many years of research, the existence of medium-sized black holes. The presence of black holes of intermediate size, lighter than supermassive black holes, which are much more frequent in most galaxies, should allow us in the future to understand how they work. An intermediate black hole is thus larger than those resulting from the collapse of a single star, but remains much smaller than supermassive black holes, which are millions of times heavier than the Sun. As in any precept, there is always an exception that confirms the rule. Black holes are no exception to this rule. Considered as cosmic vacuum cleaners, they are used to make any matter or light that comes dangerously close to their accretion disk disappear permanently. However, a black hole comes to disturb this concept. Located in the constellation of Compass, a little more than 34 million light-years away, in a dwarf galaxy named Hennes 210, an actively growing supermassive black hole of about 1 million solar masses is upsetting this stereotype. How? Let's just say that instead of tearing stars apart and causing them to gradually disappear into its bowels, it instead promotes their formation. Indeed, young stars form in this galaxy at a prodigious speed, giving large clusters of blue-tinted stars that you could admire. In the center of these star nurseries, which sparkle with 1,000 lights, we can distinguish in a bright region the massive black hole, surrounded by pink clouds and dark dust bands. But let's get a little closer to this strange object and try to understand its structure. In the near suburbs of this black hole, at a distance of only 230 light-years, a region of star formation stands out. The black hole seems to be connected to this star cluster by a continuous flow of gas, which, like an umbilical cord, comes to feed this region of space, very bright. This black hole does not eject material into space at extreme speeds, but offers a gentle flow whose speed is only about 1.6 million kilometers per hour, or 600,000 miles per hour. Thus it allows the captured and then compressed gases to be precipitated at less intense temperatures, allowing them to form new stars in even denser clusters. As you have just seen, although black holes have many similarities, some are distinguished from their fellow black holes by atypical characteristics. This is also the case of a supermassive black hole, located in the supergiant elliptical galaxy, Messier 87. To go to meet it, we must go to the constellation of Virgo, more precisely, in the Virgo cluster, which contains many galaxies, including Messier 87, which is the largest of all. This one is about 53 million light-years away from our solar system and extends over 120,000 light-years. It is therefore slightly larger than the Milky Way. However, while the Milky Way is accompanied by about 200 star clusters, Messier 87 has an incredible number. This galaxy evolves in the company of approximately 12,000 globular star clusters. The star M87 is a supermassive black hole that has been the subject of numerous observations for a number of years. A shot from the Event Horizon telescope immortalized it in 2019, supporting its fame and confirming that it is indeed the black hole with one of the highest masses of all supermassive black holes. Indeed, its mass is about 6.5 billion times that of our Sun. This black hole is 55 million light-years away from our solar system, but its particularity is that it emits a vast jet of relativistic matter that propagates over 5,000 light-years in the cosmos. The latest observations by Chandra X-ray astronomers have noted that some sections of this plasma jet are moving at a speed never before seen. It is the first time that such a speed is observed in the jet of a black hole. But what can this jet correspond to? Isn't a black hole supposed to swallow everything that comes its way? In fact, it is not so simple. Although the black hole attracts matter to the center of the galaxy, it is not completely swallowed. The matter approaching the black hole starts to turn in the accretion disk. Only a small amount is absorbed by the black hole. The remaining matter is expelled into space in the form of a jet or a beam, whose path is linked to the magnetic field lines. These jets, which are far from being smooth, are rather in the form of knots. By studying their behavior over several years, astronomers have been able to deduce that they move at extraordinary speeds, up to 6.3 times the speed of light. Yes, you heard right, 6.3 times the speed of light. How is this possible? Nothing can move faster than the universal speed limit. In fact, the star M87 did not break the laws of physics because it does not expel matter at a speed greater than the speed of light. Scientists have demonstrated that this is in fact an amazing phenomenon called superluminal motion. This movement occurs when objects move at a speed close to the speed of light, in a direction similar to the line of sight of the observer. This is in fact what is happening with this black hole. However, the near cosmic speed experienced by the particles in the jets of the star, Messier 87, is attested, reaching 99% of the speed of light. Black holes millions to billions of times the mass of the Sun exist at the center of almost all large galaxies. Like their host, they are inexorably bound to evolve and merge with each other. In order to witness this spectacle, as rare as it is spectacular, I now propose that you go and meet the vast Seyfert galaxy, located in the constellation of Hydra, 200 million light-years from our Sun. NGC 3393 is a very dense barred spiral galaxy, which in addition to being considered remarkably active, has the particularity of hosting two supermassive black holes distant from each other by only 490 light-years. One of the two black holes, monstrously large, is being devoured by its even larger counterpart. Their mass is at least 1 million times the mass of the Sun for the first, and about 30 million solar masses for the second. The luminosity given off by their two quasars is such that scientists have long believed that this galaxy, well ordered, had only a single black hole in its center. Imagine their surprise when they observe for the first time these two cosmic monsters side by side using NASA's Chandra X-ray Observatory. This discovery makes it possible to affirm that there are several forms of fusion between galaxies when they collide. While researchers have long believed that direct collisions between galaxies, known as major mergers, lead to dramatic results with anarchic and chaotic rearrangements of their structures, they now have evidence that this type of event can also occur with less turbulence. NGC 3393 confirms that minor mergers can take place. Under its calm and imperturbable airs, this galactic bulb with two synchronized hearts is the proof. You are witnessing the end of an insidious merger between two galaxies of unequal masses, whose spiral shape of the larger one remains impassive and regular. The smaller of the two black holes must have had less mass than its companion when their host galaxies began to merge about 1 billion years ago or more. Even if these two monsters cohabit harmoniously, devouring simultaneously the stars that come to them, the larger one, like a cannibal, undoubtedly nibbles its neighbor with incessant assiduity. Although this remains very complicated, new technologies now allow even more precise comparisons between black holes. If scientists have long thought that there were only two types of black holes, stellar and supermassive, it is now believed that there is a continuum and that there are also intermediate size. The latter should therefore have a mass between 100 and 10,000 solar masses. Their existence was predicted when very bright X-ray sources were found far from the center of some galaxies, where supermassive black holes are usually found. This was observed in 2006, when a strong X-ray flare from a source named 3XMM J2150 was observed by the Hubble telescope, but also in X-rays by the XMM Newton and Chandra space telescopes about 800,000 million light-years away in the constellation Aquarius. This observation was able to conclude that it was indeed the destruction of a star by a black hole, weighing more than 50,000 solar masses, hosted in a cluster of stars on the outskirts of a distant lenticular galaxy. In 2020, the Hubble Space Telescope had the opportunity to immortalize a new burst of X-rays in this same area, confirming that a black hole is indeed engulfing a star that is a bit too curious after having partially shredded it in a cataclysm of superheated gas and X-rays. If the existence of intermediate black holes has been proven by this technological prowess, on the other hand, it pushes scientists to question more and more. If they know that the mass of an intermediate black hole is between 100 and 10,000 times the solar mass, they do not understand how such a structure can form. No single star can give birth to such a heavy black hole. However, several hypotheses are emerging. One proposes that a single black hole, if it had enough matter to devour permanently, could reach such a weight. Another suggests that it could be several black holes that have merged. In any case, the formation of these objects remains one of the most interesting enigmas for high-energy astrophysicists. Black holes, like all cosmic objects, move through the cosmos at the pace of their host galaxy. If we know that some galaxies have undergone great upheavals by meeting, or even merging, with one of their many similar ones, what about black holes? What would happen if two of these cosmic behemoths cross paths a little too closely? After all, isn't it said that only mountains never meet? We will probably have the answer in a few short years, thanks to a galaxy that is about 1 billion light-years away from our solar system. This galaxy, known as SDSS J1430 plus 2303, appears to contain a pair of supermassive black holes with an overall mass of up to 200 million solar masses, whose behavior is very strange. Oscillations in the galactic nucleus, observed for 3 years, have been found to be shorter and shorter, going from a period of about a year to a period of only 1 month. These fluctuations of light detected in the center of the galaxy allow scientists to consider that 2 black holes are rubbing shoulders in this area, but more importantly, that they should undergo an imminent collision within the next 3 years. If this is the case, it will be the first time that a collision between 2 supermassive black holes can be observed. Scientists hope to see a huge explosion of light across the spectrum and expect to learn much more about how black holes work. But let's leave these 2 hellish spirals behind and take a step back. A premature collision, although it would offer us a wonderful spectacle, could be fatal. What if I took you to the brightest object in the early universe? Are you ready to reach, or almost reach, the edge of the universe, 12.8 billion light-years away from our galaxy? Put on your sunglasses. You might need them, because we are about to approach a bright quasar, whose light is equivalent to 600,000 billion times that of our Sun. Named JO 43947, this unique object shines right in the heart of a galaxy in formation during an early part of the universe's history, known as the Epoch of Reionization. The latter corresponds to the period when the universe was less than 1 billion years old, when the first stars and galaxies began to consume clouds of neutral hydrogen in the cosmos. This energetic core cohabits with a supermassive black hole that feeds voraciously on the dust and gas that surround it, producing increased luminosity due to the resulting heating. Very active, this quasar has an estimated star formation rate of 10,000 stars per year, which is enormous compared to our Milky Way, which produces only 1 star per year. The black hole does not simply absorb the diffuse gas of intergalactic space, Despite its intense luminosity, such an object might never have been observed by scientists because of its position at the edge of our universe. In fact, its discovery is largely due to the disposition of objects in the cosmos. It is a physical phenomenon known as gravitational lensing that allows us to locate it. According to Einstein's theory of general relativity, powerful gravitational forces can bend the path of light. In our case, the light of the observed quasar is distorted by a faint galaxy, located halfway between the Earth and the quasar, which has no other effect than to increase its brightness by 50 times, but also to distort the space around it. This gravitational lens then bends the light, like an optical lens, and divides the image of the quasar, so that it can be seen in 3 different places simultaneously. Thanks to this magnification, astronomers are able to observe this cosmic monster more closely, even though it is very far away. A gigantic discovery was revealed by the scientific community in 2017. A supermassive black hole, more than 13 billion light-years away from Earth, was detected by one of the telescopes in Chile in the far reaches of the universe. Named ULAS J13-42-08, this black hole is a monster that is 800 million times more massive than our Sun. It is the largest black hole ever detected in the depths of the universe. Its particularity? Its size, but especially its age of 13 billion years, which does not agree with the models currently used to describe the beginning of interactions between the first stars. This quasar beats all the records of precocity, with an immense size noted, whereas the universe was hardly at 5% of its current age. It is extremely far away and unusually massive for its age, and thus poses a problem for astrophysicists. No object can be older than the universe itself. Light travels at a definite speed. Therefore, the more distant an object is, the older it is observed. This means that this black hole was observed as it was more than 13 billion years ago, when it was very young. The universe being 13,700 million years old, ULAS J13-42-08 is therefore less than 700 million years old. Although black holes are known to be voracious, they grow relatively slowly. A black hole, in the best case, doubles its mass in 40 million years. Therefore, to multiply its mass by 1,000, it takes 400 million years and 800 million years to multiply its mass by 1 million. However, ULAS J13-42-08 is less than 800 million years old. Therefore, it should be about 1 million times less massive than its detected mass, which is 800 million solar masses. The question is, how can such a young object be so big in the early universe? 2 theories emerge. Either the growth rate of black holes is underestimated, or, and this is the most likely explanation, much more massive black holes could have formed in the younger universe than today, following the explosion of a massive star. If this is the case, we can imagine that primordial stars, probably more massive and living longer, allowed the birth of much larger black holes during the youth of our universe. This type of quasar should reveal stages of the universe that are not yet known. Among the strangest black holes of the universe, we cannot ignore the largest of them. Phoenix A and Ton 618 are to date the two most massive black holes ever detected. But let's take a closer look at what we can learn from Phoenix A, the central galaxy of the massive Phoenix cluster of galaxies, located in the southern constellation of Phoenix, about 8.5 billion light-years away. This galaxy has a star production 700 times higher than in the Milky Way, giving birth to 740 new stars every year. It is the most active galaxy ever discovered. But what makes it special is the black hole at its center. The latter is the largest black hole detected. The mass of this central black hole is estimated at 20 billion times that of our Sun. By itself, it represents nearly 10% of the mass of the entire Milky Way, and its event horizon has a diameter of 590 billion kilometers, or more than 366 billion miles. If we wanted to follow its perimeter, it would take us 71 days at the speed of light to go around it completely. Its colossal size cannot be explained by the collapse of a single star. This black hole, which deserves to be labeled as ultramassive, could in fact be the result of a collision between several supermassive black holes that were formed shortly after the Big Bang. But let's not stay too long in its vicinity. This ogre continues its exponential growth by increasing its mass by 60 suns each year. In the heavyweight category, we can also look at Ton 618, another hyperluminous quasar that measures 190 billion kilometers, meaning that it is 135,000 times larger than the Sun. Located at the border of the constellation Cans Venatici, also called hunting dogs, and Coma Berenices, which translates as Bernice's hair, it is about 10 billion light-years away from the Earth. Its particularity? In addition to being of monstrous, even unimaginable size, Ton 618 is reputed to be one of the brightest objects in the universe. Its luminosity is estimated at 140 trillion times that of the Sun, while its mass is estimated at about 66 billion solar masses. Remember that our Milky Way has a total of 64 billion solar masses. It is obviously a supermassive black hole whose accretion disk serves as a permanent pantry. Moreover, the materials orbiting close to it have a speed of nearly 7,000 kilometers per second, reflecting a very important gravitational force. Scientists estimate the age of the universe to be about 13.7 billion years, but since they have been able to study galaxies, and more particularly black holes, a mystery remains. How did the largest black holes, whose mass is estimated to be millions, even billions of times that of the Sun, become so large in such a short time? While astronomers have observed the first star-producing galaxies, where supermassive black holes probably formed, they have not yet had the opportunity to link them unambiguously. At least until the discovery of a missing link, a growing black hole still covered with cosmic dust. This recent discovery allows them to consider that there is indeed an intermediate phase between star galaxies and supermassive black holes. To better understand this theory, let's go to the coveted object, an ancient black hole known as GNZ 7Q, nestled in the heart of an early galaxy in one of the best probed areas of the distant universe, the Great Observatory's Origins Deep Survey North. Imagine the surprise of astronomers who, with the help of the Hubble Space Telescope of NASA and the European Space Agency, managed to point their lens at a celestial object that has a high probability of being a fast-growing black hole. more than 13 billion light-years away. This type of black hole, which has never before been encountered by scientists except in theories or computer simulations, could support the hypothesis that supermassive black holes originate in the dust-covered cores of starburst galaxies before expelling the surrounding gas and dust and emerging as extraordinarily bright quasars. These dusty galaxies and bright quasars, extremely rare, have nevertheless been detected at the beginning of the universe, and GNZ 7Q seems to correspond in all points to the characteristics of a young quasar in transition phase. It provides scientists with an opportunity to understand the rapid growth of supermassive black holes in the early days of the universe. Its age has been determined by scientists who estimate that it existed barely 750 million years after the Big Bang. It is therefore a newly formed black hole at a time close to the first known supermassive black hole in the universe, which is located in a galaxy forming stars at a rate of 1,600 solar masses per year. While GNZ 7Q emits very weak X-ray wavelengths, it appears bright at UV wavelengths. This suggests that the core of the accretion disk that generates the X-rays is always darkened by the dusty core of the star-forming galaxy, while the outer part of its accretion disk releases UV light. I let you imagine the luminosity that will emerge from this quasar when the galactic dust will have faded, revealing the presence of this ogre, until now invisible. Black holes are still far from having revealed all their secrets, and it is not without reason that they attract us more and more. After all, no one can say what happens at the center of a black hole. All we can say today is that the matter that crosses the point of no return is compressed to an infinitesimally small point, and that all conceptions of space-time collapse completely. This singularity has not yet found an explanation in the scientific community, even if several hypotheses are being studied, such as loop quantum gravitation or the existence of gravistar. Quantum gravitation envisages that black holes, by dint of contracting, can bounce back. This is the theory of Planck's bouncing stars, in other words, a temporary phase between a compact star denser than a neutron star and a white hole, where the space-time variable would be reversed, offering an exit door to matter through a wormhole. A gravistar, whose name means gravitational vacuum star, would be a kind of bubble filled with vacuum and enveloped by a crust of matter so hard that everything that would pass by it would be sucked in by the star's gravity before crashing into its surface and finally merging with it in a large energy emission. What about you? Do you think that a black hole is only a gigantic sidereal crusher? If not, are you ready to try the experiment? But beware, if you plan to let yourself be sucked into a black hole, no matter what happens, your trip will be a one-way trip. Worse, you could be stuck forever between two universes, completely disatomized. Even if you are lucky enough not to be disintegrated on contact with a hypothetical extremely hard shell and to be transported to the heart of a wormhole, your destination remains unknown. Do you feel ready to discover a possible parallel world with all the surprises it contains? But above all, are you ready to say goodbye to your world? Because no return to our current space-time will be possible.